workshop, then you should turn your video off because it will be shared. It's unlisted, but it will be sent out to people. So just for privacy reasons, if you don't want, that, you should, whatever you need to do for that. Also, I was going to say for introductions, I'll say that we're waiting to admit a few people, so I'm just kind of rambling right now. It's just, what is your name and where are you located? And you can put that in the chat. You can even tell me. I'm Nikki Selkin, and I'm in San Francisco. I'm typing it too. Ooh, we have someone from Nepal.
Yeah.
That's exciting. So yeah, I'm just waiting a few minutes and admitting people into the session. Steve, you're back. I feel like I've spent all weekend with you.
Almost, just some parts of it.
I know. I was saying to the last workshop teachers, Sergey, I feel like I'm saying his name wrong all the time. Anyway, that he should make you a beta tester for when he does his AR project where he makes the app have geolocation. So then you can use the location, the pictures of the buildings that you do your latest mandalas of, and make a walking tour. That was my plan for you, by the way.
Yeah, no, I was thinking about that sort of stuff. And it's a great tool, actually. I was really thrilled by how simple it was to use and how good of an interface I have for it. I'm going to be dodging out of this a little early because I have to be somewhere by 6. So I'll just sign off quietly around 5:15, 5:30.
Going somewhere in real life.
I'm going somewhere in real life, yes.
Oh, yeah, that's so cool. Oh, you were in I just saw in the chat that am I saying your name right? Nasala? You were in in the Amplify session. Were you in the one where I did grants or the one where I did everything else? I don't know. Yeah, both. So you've had your fill of me, I'm sure. And all my crazy backgrounds. Yeah, I also teach workshops, which tend to happen during our festival with 01 that runs our American Arts Incubator. That's an exchange program between American artists and international artists that happens every year. And it's such a cool program, and I recommend everyone apply for it. I've never done it, but I help mentor within it, and just really great stuff. Once again, everyone, we're just introducing ourselves on the chat, what our name is, where we're located. And I will remind you again, I am streaming this to an unlisted link on YouTube to share with the festival participants who have audit access, and also for recording, which I can also share with you if you want to review the workshop after we take it, if you missed anything. I know that I often forget things and want to go back. So we're trying it for not the first, we definitely live stream quite a lot of gray area, but we don't, I haven't tended to do it with workshops, but we're giving it a shot and seeing how it will go. So yeah, I'm just waiting for a few more people. We're at 16, so we're almost there. Ooh, Boston, LA, San Francisco, Colorado. Here's one more person. Nepal, Oakland. I know I'm going to move to Oakland, so need your advice. All right. Hi.
Hey, Shri.
Hi, Soma.
Hello. Glad you could make it.
Me too.
Okay, we're almost toward capacity, I think. We're not, but we could start. Okay. it's 5 after, so I normally start my little introduction there. I'm Nikki Selkin. I am the Gray Area Creative Development Director, which basically means I run all the arts incubator and education programs, as well as do some curation and exhibit design for immersive exhibits. By my own practice, I do actually not dissimilar from what Soma does. Like I do processing and teach P5JS. Also teach wearable technology, which also you do. We have like a lot of crossover. And like physical computing. And he and I were both in my first experience with Gray Area after moving back here from New York. We both taught in the what is it called? It was like a mentorship program that we took youth and we taught them and mentored them and helped them make an art project. And you did yours at Hunter's Point, and I did mine at Dolby with a group of girls, co-led by Shelley Sherman. And that's how we first met a long time ago. So let me just say about Gray Area. Gray Area is a nonprofit located in the Mission District of San Francisco. We have a single screen cinema that's been kind of revamped into a giant open space art gallery, venue, just kind of everything. There's an incubator, there's a music studio. We have another different kind of artist studios there. And our whole mission is to apply art and technology to create civic and social impact through education, incubation, and public events. And since COVID started, we've done, I think, over 100, I want to say 150 probably with the festival, remote events, including, it's crazy. We just haven't stopped working, including concerts, multimedia, live stream shows, workshops. I have myself staged 2 3D gallery exhibits using what's called New Art City. This guy, Don, who's been amazing to work with, which I can tell you all about later, as well as this. So, I did the festival gallery and then also these workshops. So really excited to join you. And personally, if anyone needs or wants to teach, you can always reach out to me, try to get you a workshop going. Or if there's something you want to learn, let me know and we can try to program it. The incubator is called the Gray Area Incubator. I'll put a link in the chat. Steve Pye is in this workshop, and he's a pretty long time member of the incubator who does some really, really interesting work, and who originally came to us through the immersive Creative Code immersive program. The other incubator I mentioned was 01 Incubator, which is the American Arts Incubator, and I'll put a link. Let me find it. I just have to look for this one because they're located, they're sort of a partner organization with us, housed within our building, but theirs is more of an international incubator and ours is more local. So we work with local artists and they work more with international. Anyway, that's my spiel. Oh, I have one more thing to say. I have to say, again, for those of you who just joined us, this is being live streamed to a private link that will be shared with festival participants who purchase an auto access tier. However, I can also give you the live link to the live stream recording link so you can review the workshop at your free, at your leisure later. And we'll probably do a follow-up email with all of that info. But the other thing I wanted to say before I go is go to handing it over to Soma. I'm actually going to put myself in speaker view and pin myself right now. We have a code of conduct, and we are committed to providing a friendly, safe, and welcoming environment for all, regardless of race, age, gender identity, and expression, sexual orientation, disability, perceived appearance, race, ethnicity, age, religion, or nationality. And we expect everyone to treat each other with respect and just be mindful of your behavior, even in this digital space. I also just personally want to point out that the technology space has often been historically a place where women, people of color, and queer people were often marginalized. And I acknowledge that and want to make sure that that is not going to happen. I know it won't happen, so I trust everyone here. At any time, if you feel uncomfortable, feel free to reach out to me during or after the workshop, and we'll talk about it. And yeah, but I'm not, I'm thinking it's going to go wrong. Just want to say that and make make it be known this is a safe space. And we really try to make it a safe space. And part of that too is if you want to change or put your gender pronoun into your name, you can click on mine's a generic name because I'm using our live stream account, but you can click on your name and you can put she, her, they, them, he, him, or whatever your pronoun of choice is. I think that's all my announcements I have. And with that, I will also say, please mute yourself when you are not talking. I'm going to pin the instructor to the video, but if you don't have muted, it might try to like show you like eating chips instead of the instructor. So just mute when you're not the main speaker. Thank you. And here we are, it's a holiday.
Cool. Hello, thank you. Yes, I want to second that gray area is awesome. It's one of my favorite things that's happening in San Francisco. I'm really happy that you're all here supporting it. I know times are hard for everybody, so it's really cool that they've been able to put on so much content. And I'm grateful. That's why I'm able to talk to you guys. So, hi, I'm Soma Holiday. You're probably here for this workshop. I'm actually going to share my screen. Let's see here. Boop, boop, boop. All right, you guys able to see my?
Yes.
Cool, brilliant, thank you. So this is the workshop. I'm going to be going through the slides on slides.com. I'm going to paste a link in the chat real quick. It's going to link to a page on my website that has some links to resources, including the slides that I'm going to be going through and the code samples that I'm going to be going over. If you click the link that's on the site to go to the slides, it's going to bring up a live view that will automatically update as I go through the slides, which is pretty nifty. You can either watch it through that mechanism or through my screen share. I'm going to be sharing it on my screen as well. But the advantage if you're following on the actual live version, you can click links. So that might be useful for you. But yeah, if you could try that out, let me know how it works. This is my first time trying it, but it seems pretty cool. So let's get into the workshop. Who am I? Why are you here? I am Soma Holiday. I work, like Nikki mentioned, in a similar space, using technology as a tool for being creative. My specialty is LED installations, and I also dabble in infinite loops. So that's probably more relevant to why you're here. So if we take a look at some of the stuff that I've done, it's my website, which was so close to being updated with the whole new design just in time for class, but check back in a week or so. You'll see some of the later projects that I've been working on. But yeah, I'm a freelance software engineer, LED artist, creative coder, and educator. I work on interactive LED installations like these. These are some of the smaller ones. Then I'll show you some of the larger ones that I've been working on this past year. And then animated GIFs and movies that I post on Instagram. So this has kind of been, I've experienced a renaissance of this during COVID times. So I'm really glad that I can share with everybody what I've learned during that time. And then some of the larger installations I've been doing is here's a large scale LED installation in a bar in Las Vegas. Here's a giant disco octopus that's audio reactive that we did for a club in Las Vegas. And then last year I had the opportunity to work on the temple for Burning Man, which was really an amazing educational experience. So yeah, that's kind of what I've been up to. Again, this is the site that I sent you to. Hopefully everyone was able to get that link working. Oh, there's also going to be a chat. I created a room on the Matrix chat for a gray area that's seamlessly looping art. I'm not going to be checking it during this class just because I imagine not everyone has had a chance to sign up for it. So for the duration of this class, let's stick to the Zoom chat. I'm going to be checking that for questions periodically. But afterwards, please all join that, and I'll be happy to answer any questions that you have in there after the workshop.
And I will put a joining information guide because it's an open source platform server, so it can be a little tricky. But I'll help you if you have any questions, and I'll send you that tutorial.
Yeah, and then this instructions links probably to the same thing that Nikki is referencing. So when you're
God, you're such a good teacher. You already know.
Glad to hear it. Yeah, so I'll share out these slides, not the live version. I'll update the link so that everyone has access to these slides afterwards.
Thank you.
You can follow those instructions. But before we start and talk about technology and stuff, I want to thank you all for joining. There's a lot of ways you could spend your Saturday. So I'm really honored that this is how you would choose it. Sunday? Today is Sunday. What is even a day? Sunday. But before we go into it, the world is extra weird right now. I want to acknowledge that, particularly in the US. It sounds like we have some people not in the US, but a lot of us are. So I thought it'd be a good way to start is just drop 1 to 3 words into the chat about how you're feeling today. We've already gone over where you're located and your name, but just in 1 to 3 words, what's on your mind? How are you feeling? I'm going to go ahead and put mine on there and say I am fatigued but optimistic. Content, relaxed, enthusiastic, learn. Awesome. That's good to hear. Tired but excited. Open to interesting distraction. I hope that I can offer that for you. Just wait a couple more seconds for anyone else that wants to join in with their 3 words. Wanting to learn and do more. Excited, jittery, sore. Cool. So yeah, it sounds like we're all roughly on the same space. Apprehensive and creative, just feeling present. Cool. Thank you for sharing. That's awesome. Yeah. I just want to acknowledge, things are weird. If you're feeling weird, that's probably normal. Cool. So with that, we'll go over what we're planning to cover today. So I'm going to break it down into 3 main sections. They're not going to be evenly weighted by any means. We're going to go through how to produce, polish, and package, because alliteration is cool, animated loops, so seamlessly animated loops in particular. So first we're going to focus on some techniques for producing, and this is going to be the bulk of the course. We're going to introduce everybody to processing. I know we have a wide spectrum of experience levels with programming and processing, so I want to make sure this workshop is valuable to everyone. We're going to go through some of the basics on processing, how animation works, how to work with colors in processing, how to control the flow of time in processing, which sounds pretty cool, and it is a really powerful concept. And then we'll take a look at some of the secrets for making loops. What is the secret of the loop? Fun with trigonometry that ties into the secret of the loop. And then a few other techniques that I use in a lot of my pieces. Cascading, using noise effects to add more natural organic movement. Then we'll take a look at some techniques for polishing. So take a look at blend modes and how you can get more out of the colors that you use. Easing to control the rate of motion in your animations, and the motion blur to make it look more natural. All of these are kind of geared towards making things look more like you would expect in real life, as opposed to something that was drawn by a computer. And I've been working on animated GIFs and processing for many years, and I was always kind of frustrated that I would see these artists who are coming up with this. I knew they were using processing as well, but their output looked so much shinier and nicer than mine. And these are some of the techniques that once I really internalized them and put them into use, I found really leveled up the visual interest and got me more to that level that I was chasing. So hopefully you can get something out of that as well. And then packaging. So once we've actually generated all of our animated frames, how can we take those and bundle them up into an animated GIF or a video, and specifically suitable for sharing on social media. So Twitter and Instagram are really popular social media platforms that you may have heard of. And that's where I share my material, and I'll go over the processes I use to get there. And just a note, all of my experience with these tools is Mac specific. They are all cross-platform, so they should work, but your mileage may vary on Windows or Linux. Then just a little bit about how the class is going to be structured. So periodically, you're going to see 2 different emojis. This is the pause one. So this is just a note. This is my first time teaching remotely over Zoom. So I'm missing some of the normal feedback mechanisms that I'm used to, like raise your hand if you're familiar with X. I'm going to build in pauses to go and take a look at any questions that anyone's posted in the chat. That's what these pauses are for. And again, we have a wide range of experience in this class, so feel free to help answer each other's questions too. If someone asks a question that you know the answer to, we can build a community here. And then if you see the play button, that's where we're going to go into breakout rooms and take some time to experiment with some of the topics that we've been covering, give everyone a chance to either talk about the stuff that we've been learning or actually go heads down and code on it. I've taken a few different online courses during COVID. Oh, so it looks like someone's emojis didn't show up quite right. Well, it should be a play and a pause button. I'll call it out just in case it's not displaying properly for you. But yeah, I've taken a lot of online courses during COVID, and the breakout rooms in groups of 3 or 4 I found really work really well. And then people in those groups can kind of decide if they'd rather talk about the content and just start to make a friend, which I've had happen, or if you just want to sit down and spend some time coding on the stuff that we've been going over, or if you want to take a break, go get some water. All of that is open to you. So a few notes about learning, my approach to learning and my thoughts on learning. Learning is hard. Learning is really hard. It's inherently uncomfortable. You're doing something that by definition you've never done before. So that's okay. It's pretty cool that you're brave enough to try it. And I want to thank everyone that filled out the survey to give me a sense of everyone's relative experience levels. I know that as I mentioned, we're all at different levels. What's hard for one person may be easy for someone else and vice versa. So be open to that. And if you find that something is coming easy to you and is challenging someone else, try and offer them a hand if you can. And I did see someone said that they had 0 programming experience in the survey, and this class might be tricky for you. I do want to set forth the understanding. I'm not going to be going over any programming fundamentals. So I'm going to assume that you have familiarity with variables, functions, and loops. This is all going to be in Java, which means it's a strongly typed language. If you're used to JavaScript, it's not strongly typed. I can point out where that's going to cause a little bit of friction, but it should be okay. It doesn't assume any processing experience, so I'm going to start from scratch with processing, but base level programming knowledge is something I'm going to assume. This is a safe space. I'm really glad that Nikki called out the code of conduct. I strongly believe in that. And you should feel safe asking questions if you don't understand something. And you can ask, like I said, you can ask questions of each other in the chat or the breakout rooms and take advantage of the fact that we have a wide array of experience levels from people who are just getting started with programming and processing to people who are professional software engineers. Feedback is a gift. So my take on teaching is, as a teacher, we're basically making educated guesses as to how best to get this content across to you. So feedback is a gift that helps us figure out what to focus on. And like I said, again, this is my first time teaching on Zoom and my first time teaching a lot of this content. It's going to be a pretty dense course. I would probably normally split this up across several sessions. So it's a lot. Be prepared for that. We might not cover it all. It might not all make sense in the first pass. Let me know. That'll help me make it better for the future. It'll help me go through and answer any questions on areas that maybe people didn't think I did quite so hot a job on. That we can take advantage of the matrix chat afterwards. And the good news is, no matter how far we get through the slides or whether or not it makes sense in the first pass, you get to keep these slides. And there's going to be a whole bunch of coding exercises and code samples that you get to keep no matter what, to go over as many times as you like in the future. And you can always drop me a line. So the structure of the course is going to be some slides, but mostly coding along. And I'm going to be coding and explaining what we're doing. Some notes on coding along. People have different attitudes towards the value of coding along. If it helps you, do it, but don't feel obligated to code along as you're watching me. You can just watch, because all the code is going to be shared at every coding exercise. There's going to be a link that's going to point you to the end state of the coding exercise that we're doing. So even if you fall behind, if you want to try it on your own and you fall behind, you can click on that to get all caught up. And most of the lessons are going to build on top of each other. And I recognize too that coding along can be a dangerous format, because I'm sure we've all watched these tutorials on YouTube where someone who's a savant that's been using an environment for 20 years can whip up this masterpiece in like 5 minutes, and then you're just like, what just happened? So I've been doing this for a while. I want to make sure that I don't jump ahead too much, but if it does start to feel that way, please call it out, let me know. And I want to make sure that this time is as valuable as possible for everyone here. And then again, I encourage everyone to revisit these coding exercises. They're designed to be revisited and objective driven. So with that, that's my spiel on how the class will go. Let's talk about the art form of the infinite GIF. I'm going to show some examples and why I like it. So it's a really interesting art form. It kind of focuses on the infinite loop, which typically has like a hypnotic or captivating quality that makes you want to stare at it for a while, which I find really endearing and exciting. I think they kind of took off as an art form in Tumblr around like the early 2010s, 2011, 2017 or so. There was a lot of artists just sharing infinitely looping content that was interesting like this, often generated with environments like processing, but there's some other ones too that I will go over a little bit later. Wave Grower is one of those artists. He's a French artist who has an interview linked here where he talks about his motivations and inspirations for this kind of art, which really align with mine. He's inspired by natural motion that he sees in nature, like this rippling pond effect. This one focuses on a more traditional sinusoidal waveform, which we'll take a look at. Bees and Bombs, he's one of the patron saints, I would say, of this art form. He has a really unique and identifiable style. It's very organic and kind of this trippy MC Escher illusionist style. He's also incredibly prolific, and he shares a lot of his code. In fact, at the very end of this course, I'm going to be sharing a template. It's kind of like the main bit of swag for this course that is a starting point for making beautifully animated GIFs. And that template is based on his work. Most of the things I've learned are based on the shoulders of giants in this area who have been sharing their code and helping us all learn. Etienne Jacob is another one of those artists. Oh, it looks like the slides did not update. Oh dear. Let's try and reload that. Whoa, technical difficulties. Let's see. Well, that is unfortunate. It looks like the view of the slides is not updating when I jump back and forth. Forgive me one moment. Let's see if we can figure out what's going on here.
It's okay.
Ah, I see what happened. The log, so I'm using slides.com and the authentication timed out. So I'm not logged in anymore. Neat. One moment. Let's try this again. All right, cool. Back in business. So Etienne Jacob is another patron saint in this area. He has a ton of amazing tutorials that I'll be sharing throughout this. He specializes in purely black and white imagery and really organic feeling. So this looks like it's chaotic and random, but it does in fact infinitely loop. And so we're going to take a look at some of the techniques that he uses to get that natural organic feel while also maintaining a programmatically structured loop that we can guarantee looks the same at the beginning and end. So processing is one tool that people use for this, but there are other environments like Cinema 4D, which more specializes in higher quality 3D rendering. Processing does have some 3D capabilities, but its rendering is limited. So if you want to do some more sophisticated and pretty rendering, you want to go with something more like 3JS or Cinema 4D. Hexiosis is another prolific artist. He uses a combination of Cinema 4D and Adobe After Effects, which is another popular tool for doing this kind of animation. He's got a very distinctive style, this really trippy portal style. All of his pieces are always traveling through this portal with a lot of hexagons involved usually. But then there's tons of other ways and tons of other manifestations of infinite loops. Oh, I see this one is not infinite loop. There we go. By our own Nikki Selkin. So she has a series called Unattainable Landscapes, where she does these really cool impossible dreamscapes. And it feels much more organic using actual live footage. And she doesn't use any of the tools that I just mentioned.
I know. It is my iPad game. Like, I got an iPad for teaching at the Apple Store, and then I broke my foot, and then it was COVID, and I was like, what am I going to do with this iPad? And then I constricted myself to only using the iPad to make them. And so while I was like laid up with my foot broken, I made a lot of them. I'm not trying to interrupt your flow, but someone did ask me. First of all, thank you so much for showing me. I feel so flattered. Second of all, I might need to look at your room you made in Matrix because it doesn't allow me or anyone else to log into it. But just we'll worry about it after. But I just wanted to say for people, don't worry, we'll fix it and make it work. That is
Sounds
all.
good.
But thank you so much.
I will take a look at that afterward. Cool. Yeah, and I did want to call out, I love that is Nikki's constraint, is that it has to all be done on an iPad. That's really cool. I think constraints can be very productive. This is another one. This type of infinite loop that's based on real footage is typically called a cinematograph. So if you want to Google for techniques to create those, use that term, you'll come up with some good stuff. This was built by an artist called Lens of Adventure using an app called Fixel, which I think is also an iPad app. So yeah, that's a whole bunch of animated GIFs. So hopefully that gets you excited about the stuff that we're creating, sets some context about what we're doing and why I like it. I think it's just a really cool art form.
I'm so excited. Sorry, I keep popping in like a creepy voice. I'm just really excited.
No worries.
Like, that's why I programmed this, obviously. I'm very excited.
Cool. So let's jump into processing. What is processing? I think a lot of us are at least passingly familiar with it, but I'm going to start from the beginning just so everyone's on equal footing. Processing builds itself as a flexible software sketchbook. So it's an environment designed to make it really quick and easy to generate graphics on the screen. And it's designed to make programming accessible to a wider audience, specifically artists. That is their ethos, was how can we make the friction from going from 0 to animation on the screen as low as possible. We're going to be using the desktop IDE for it, which is based in Java. Though there are modes that you can drop into in that IDE to write in other languages like Python and JavaScript. There's also a separate tool that I think I saw from the survey many of you are already familiar with called P5.js. That is not exactly the same thing. It's based off of processing, so it's got a lot of the same functions, but it's it's a JavaScript library, which means it's a little bit easier to share your content directly, so you can run the sketches directly in a browser. Whereas with processing, you're going to be running an application, or using the techniques that we go over, you can take your output and render it as a video or a GIF to share. So I mentioned some related toolkits. It's a creative coding toolkit. P5.js is another one in JavaScript. Touch Designer is a crazy powerful one for people who would prefer to do their programming in node-based visual drag and drop and connecting nodes. It's a different style of programming from writing lines of code, but you can get some really amazing output, and it's really performant. So a lot of DJs and or VJs and live installation performers use it. OpenRender is a newer one. It's written in Kotlin, which is another Java JVM language. And there's Open Frameworks in Cinder, which are C++ languages. I've kind of listed these in my perceived order of complexity and difficulty in getting started with. So I think processing is the simplest one to get started because it's designed to be that way. Those other ones might be a little bit more powerful, but there's a little bit more overhead involved in getting started. And that comes across in their philosophy comes across in the terminology that they use in processing. The programs aren't called programs, they're called sketches. It's meant to mimic the act of having an idea, sitting down at your paper and just sketching it out as quickly as possible. Just get going. Get the software out of the way. So let's take a look at it. I'm gonna switch over to processing. Cool, I'm gonna actually put this on a different screen. If it lets me put it on a different screen. Neat. Cool. So I'm going to open up a demo sketch. Well, first of all, here's the IDE. This is where we type our code. Up here we have run and stop, or you can hit Control or Command R to run it as well. If we run this, it's going to pop up a window that represents the sketch that's running. In our case, we didn't write any code, so it's just popping up a blank screen here of 100 by 100. But eventually we're going to write some code and see what it can do. But I'm going to show you a demo sketch to show how animation works. So, yeah, cycle. So this is a little sketch that I put together to show how animation works, right? If you think of animation like a film strip, which is actually how it initially worked, is how movies work, is it's a series of still frames that are played back at a rate fast enough that your eye perceives it as movement. So that's what processing allows us to do. So if you see in this example, we've got the frames of the character from the video game Braid running. And if I push right on my arrow keys, it just switches from one frame to the next very slowly, but it's always a static image. But if I push spacebar, it plays it as fast as possible, and suddenly we have this illusion of him running. So a note about how fast it needs to go in order for the brain to perceive it as fluid. 30 frames per second is about when your brain will kick in and say it doesn't look super jittery. We aim for 60 frames per second. Processing is going to try as hard as it can to get up to 60 frames per second. And you can see I'm running some other stuff on my computer, so sometimes it slows down and jitters a little bit. But that's how animation works. We're going to be generating an individual frame and playing them back in order to make it look fluid. And so if I switch back to the slides. So we'll take a look at the basic functions that processing gives us in order to enable that behavior. The two main things that every processing sketch is going to have are these two functions, setup and draw. So setup is your initial setup for your sketch. It's going to be run once at the beginning to set up anything you need to set up, like colors or variables. And then the most important thing is going to be this call to size. That's what's going to determine how big the window is that processing draws for you. If you don't specify that, you see it specify where it produces a 100 by 100 window by default, which is pretty small. It's not super useful. And then the other function is draw. And what draw is going to do is going to get run over and over and over again as fast as possible, like I mentioned, aiming for 60 frames per second, with the goal of having the output of that draw appear as an animation when you run the application. So each time that draw runs, everything that gets drawn into the canvas during that draw will generate one frame that gets shown to the user. So how do you draw? Well, there's also a bunch of built-in functions for drawing things onto the canvas. I've kind of grouped them by relatedness. So we've got ellipse and circle. A circle is a special ellipse that has the same width and height. A rectangle is a rectangle. A square is a special rectangle that has the same width and height. And then we've got some functions for drawing points, lines, triangles, and quads, just by specifying the XY for a single point, XY for the start of a line, and the XY of the end of a line. And then if you supply 3 points, you get a triangle. 4 points, you get a quad. There's also some special values that processing gives you that you can reference in your code, like width and height. So width and height are going to be variables that are equal to the size of the width and height of your canvas based on the numbers that you passed into size. And the mouse X and mouse Y are super useful because they will give you the location of your mouse in X and Y while the program is running. So we'll take a look at that pretty quick. And don't worry if you don't remember that fire hose of functions I just threw at you. There's a processing language reference that you can click through here, and it'll give you a list of all of the built-in functions, how to use them. There's some examples. I encourage you to go explore it, try them out. If there's a function that you don't understand, give it a try and see what happens. Like there's really no harm in getting something wrong here. Accidents can actually end up being kind of interesting in processing. I've had some times where I sit down and try and code something in my head and I have a bug, but the bug actually generates something pretty cool. So it's the worst that happens is you don't get what you thought you were going to get. I also want to call out that there are built-in examples in processing. So if you go up to File, Examples, it'll bring up this folder view of all of the built-in examples. These examples are, in my opinion, far better than the examples on the reference. The reference is good for getting a list of all of the functions that are available, but to understand how they work, I don't think the examples on the website are super great. So I would encourage you to go check these out and play around with them. That's the other cool thing is they're interactive. You can change some numbers and run them and see how that changes and can build up a mental model for how the topics that it's presenting actually work. And one more bit of the fire hose before we jump back in and actually start coding is a note on coordinates. So if you remember from your 8th grade math class, coordinates typically start in this way. X is going increasing to the right, and Y is increasing to the up while going up. And 0, 0 is at the bottom left, right? And then we've got some negative numbers too. But this is the area that you're used to working with positive numbers. Computers don't work that way. Computers start from the top left, which if you think about it, it kind of makes sense. That's where Windows start. That's where the control buttons for Windows are located. And if you resize it, you're dragging from the bottom right. So just keep in mind, as we're doing this, 0, 0 is always at the top left. And as you increase Y, it goes down, not up. I make that mistake all the time. That's why I want to call it out. So take a quick time check and see if there's any questions. It looks like there are not any questions. Cool. Looks like we're in good shape. So let's draw something. Let's stop talking about programming animations and actually program some. So this is how the code along exercise is going to be structured. I'm going to have a little prompt here, and then if you click this link, don't click it yet because it's cheating. That's going straight to where we're going to be. But it'll show the output, the final state of these code along exercises. And so these are designed so that you can come back and look at these slides later and look at the prompt and try and do it again from scratch. I think when you're doing it, another danger of doing code alongs is in the moment when someone's explaining the concepts to you as you go, you're like, wow, yeah, this makes perfect sense. I think the real learning comes when you sit down a week later and try and cover those things that you thought you learned, and you realize, wow, I don't remember how that got started. So come back and try and use these to refresh your memory. And with that, yeah, let's jump into processing and try and make a 200 by 200 rectangle that follows your mouse. So I said the first, real quick, just in the chat, is this text big enough for everyone to see?
I would increase the size a little bit, maybe.
Increase, okay. Let's try 30. Doesn't look like it actually got bigger.
I think you have to redo a new window.
36. Oh, there we go. I think it just has to be one of their
there you go. Okay,
set
cool.
values. Cool. So I said we're always going to have a setup and a draw function. These voids, this is a Java-ism. Functions always have to specify what their return value is. These functions don't return anything, so the way that you say that is void. And we're going to call size. So let's say it's 500 by 500. And just to double check that we're in a good space, let's try and run that. Cool. So now our window is no longer 100 by 100, it's 500 by 500. We said we wanted to draw a rectangle. And if we take a look at the, I'm not going to open it up real quick, but just if you were to take a look at the processing documentation, you'd see that it expects parameters. Actually, down here, it's telling me what it expects. It expects 4 floats, which are decimal numbers. And those floats, by default, are going to be the x, y of the top left corner of the rectangle, and then the width and the height of the rectangle. So we said that we wanted our rectangle to be 100 by 100. Just to show that this works, let's say it's at 0, 0, so it's going to draw from the top left corner. Look at that, we've got a beautiful rectangle. By default, it's got a black outline and a white interior, but it's 0, 0 is the top left corner, and it's 100 by 100 pixels. We wanted it to move the mouse, or move with the mouse. So we have these special values I mentioned, mouse X and mouse Y. And if we run that and move our mouse over it, wow, now we've got a rectangle that's following us. And look how quick that was, right? From 0 to an animated, an interactive animation in like a minute. This is cool. It's got this weird tracer effect. Let's take a look at what that's about. You might like that. By default, this is what it does. But yeah, so now we've got a rectangle that follows our mouse and is 100 by 100. Go back to our slides real quick. And yeah, what's with those tracers? So we have to think about how processing works. So processing is going to keep running draw, and it's going to keep taking what the results of those that draw function and printing it onto the canvas. So anything that's done with the canvas previously is still there. So we drew that first rectangle, then we ran draw again to draw the next rectangle, based on our mouse movements. The old one's still there, so they just keep piling up, which kind of looks cool. If that's what you're after, that's an effect that you can get for really cheap. But if you don't want that, if you just want to see the rectangle, you need to clear the canvas with background. So I'm just going to go real quick and add that to our sketch. Background is another special built-in that takes in a color. For now, I'm going to put 0. 0 means black. I'm going to take a look in a second at how those colors get interpreted. Cool. So now what's happening here? Every time we run draw, we're first putting just a wash of black over the entire canvas, and then we're drawing the rectangle. So now we are basically eliminating all of those past draws of the rectangles, and we only have the one that's following the mouse. So yeah, we've got this background 0. What's that about? Let's take a look at how colors work in processing. So colors by default, excuse me, just some water. Colors by default will take 1 to 4 parameters, and those parameters go from 0 to 255, which is just a special number in computing. The functions that take colors are going to behave in this way depending on how many parameters are passed in. So if you only pass in 1, it's going to interpret that as grayscale. So I did 0, which means totally black. If I were to go to the top of that scale from at 255 for grayscale, it's going to be completely white. If you take 2 colors, or 2 parameters, then it's going to be a grayscale value and alpha, which is how transparent or opaque is it. Again, if you put alpha at 0, it's not going to show up anything at all. It's going to be completely invisible. 255 is completely opaque, and if you did like in the middle, 128, it's going to be halfway transparent. You're going to be able to see through it to whatever was drawn underneath. If you supply 3 parameters, then it's going to be RGB colors by default. Oh, wow, I got these backwards. It says red, blue, green, but it's actually red, green, blue. And then if you supply 4, it's red, green, blue, and alpha. And we'll see later why I said by default, because we can actually change that, but we'll take a look at that later. There are some other color functions that it offers besides background. So we have stroke, which determines the outline of a shape that we draw, which you might be familiar with from other graphics environments, like Adobe Illustrator. Fill, which is the fill. And then you can also say no stroke or no fill. And that will remove the stroke and remove the fill. Something to keep in mind about how these work is that it's like picking up a pen. So when you say stroke red, it's like you're picking up a red pen. Everything that you draw with that, from that point on, is going to be in red until you make another call to stroke or fill. So that's just something to keep in mind, that once you call it, it's basically setting that color context for the remainder of your function calls. We'll take a look at how we can play around with that a little bit later as well, but it's something to be aware of. Then you can also create color variables. So we have this special color that we can pass in. In this case, it's RGB, so it's just going to be fully red, no green, no blue. And we save that color to a red, and then we can reuse it. So we can call fill with that same red color and the stroke. Those are going to be the same colors. Cool. So that's a primer on colors. Now let's move back to making a rectangle that moves without our mouse. So we want to make the 200 by 200 rectangle. It starts in the top left corner and moves to the bottom right. So the way that we're going to want to do that, we want to keep track of the location of our rectangle across different calls to draw. So that makes me think of a variable. Let's keep track. Let's keep track of an int that is the x coordinate for let's call it rect x. We'll start it at 0, and then we'll also do a rect y. And then we'll just use that to keep track of the top left, or to maintain the state of our top left and top left x and y coordinates for our rectangle. So if I run this, right, we've got our rectangle again at 0, 0, because it's just looking up that value. It's 0 for x, 0 for y. We could, every time we go through our draw function, we could increment that. That's the power of having this in a variable. Let's actually, this is a special operator, means plus equals. It takes that value and adds to it. It's exactly the same as doing this. So let's move increment x by 2 every time that we draw something, and let's do the same for y. And just to demonstrate that this is the same thing, I'll use both versions here. So these are exactly the same. They're both just adding 2 to that value. So now if we run this, every time we run the frame, it's jumping down 2 pixels. 2 pixels to the right, 2 pixels down, and it just keeps going right off the screen. So this number keeps keeps going higher and higher. It's just now it's higher than 500 by 500, so it's like drawn way off the bottom right here. So that's exciting. We don't get to see it, but that's what's going on. So that's how we can actually keep track of some state across frames to move them and get some animation, right? So this is our first actual self-running animation. But if we go back to the slides again, it's not that cool that it goes off the screen, because then our animation is over, right? It's still running. It's doing, the computer's doing all the work to figure out where that rectangle is, but we don't have anything exciting to look at about it. So how do we keep it from going off the screen? So let's go back to processing and keep it on the screen. So one thing that we could do, we have that special value width and height. So we know that if the x coordinate for the rectangle ever gets higher than the width, it's gone off the side of the screen. And if y ever gets taller than the height, it's gone off the bottom of the screen. So let's actually put some checks in place to check when that happens. Right? So if rect x is ever greater than width, or if rect y is ever greater than height, that means we've gone off the screen. This is just a way to add comments to yourself, which I highly recommend doing, because you'll think you're going to remember what your code does, but your future self will thank you when you realize you don't remember what it does. So if we've gone off the screen, let's just start it over. Let's put, I keep calling this x and y, but it's rect x and x, y. Let's just start it over back at the top. Right, so now we're going off the screen. Oh, and as soon as we get off, we actually start over. Cool, so this is our first loop. It's an infinite loop. It's not seamless, but it is an infinite loop. And let's just go over what we've done here. So we're incrementing this x and y coordinate until we get off the screen, and we're always checking after we've incremented it to see if we have gone off the screen, and then we're restarting. I'm just going to point out another way to specify this that is going to come in handy later on in the workshop. Another way to keep a parameter that's constantly going up within some bounds is to use this operator called modulo. It's a %sign. So another way that we can do this is just to take the current value of x and modulo it by width, and do the same for y with the height. What modulo does, I'm going to comment this out, so that means that code is no longer running. I'm just going to demonstrate that this does the same thing, and then I'll talk through what it's doing. Okay, cool, so it's the exact same effect. It's a little bit less code, it's a little bit more expressive. The way the modulo works is it's the result of dividing this number by this number, and the remainder of that. So if you think about if rect x ever goes above 500, 500 let's say it's 502. If you divide 502 by the width of 500, you're going to end up with a remainder of 2. So it's going to start over counting from the beginning of that range. So this is a really useful way. You have something that's counting up constantly, which we're going to have a lot of in this workshop, and you want to keep it within some range, then you can just mod it by that range, and it will always start over. Cool. So go back to the slides. So I built in a time for a breakout room. Actually, I think I'm going to move this breakout room a little bit further, so we cover a little bit more about passage of time, and then we'll do a breakout room. Just a quick time check. Yep, looks like we're running a little bit behind, but I'll try and speed things up towards the end because we do have a lot of good content here. So yeah, we've now got a loop that's infinitely running here, but we don't really have control over the way time flows, right? It's really up to processing how that time flows based on how many times it calls draw. And this, I want to call out, this is my favorite title in the whole workshop, Mastering the Passage of Time. It sounds kind of awesome, like Doctor Strange level magic. So what do I mean by mastering the passage of time? So like, can we answer these questions about the sketch that we've just written? Like how much time has passed in our sketch? Where will the rectangle be? And how long will our loop take to complete? These are really important questions, it turned out, to be able to answer to create infinite loops. Like if you imagine a movie or a song that's got a playback bar, like at the bottom of your Netflix or YouTube, you can drag that scrubber to any point and Netflix or YouTube know how to jump to that point in the media. Right now, we don't have that power, and it's going to be really useful to have it. We have an implicit link. We'll take a look at that in just a second. Let's answer these questions in order, right? How much time has passed in our sketch? What mechanisms do we have available to answer that? Well, we have something called frame count. This is another special attribute or another field that processing gives us that tells us how many frames have passed since we started running the program. But these other ones we can't quite answer yet. So let's take a look at that. Let's go to our next code along exercise. We're going to move the rect, but we're going to move it such that the position is a function of frame count rather than just being incremented every time we run frame or run draw, right? So, right now we're just incrementing by 2 every time. Well, if that was a function of frame count, well, actually first, let's take a look at this special value of frame count. Println is something that will allow you to print out values to the console down here at the bottom of processing. So I'm going to print out frame count. You see the special words that are built into processing show up in red. Your colors might look a little different. I've got a theme applied, but they should show up as a different color. And then when we run it, look, it's just counting up. So we're running draw over and over and over again. Every time we run it, frame count is incremented by 1. So I mentioned that we have this implicit link between the X and Y coordinate and frame count. And that is that every time we run increment frame count by 1, X and Y get incremented by 2. So let's use that. And rather than just incrementing rect X and rect Y by 2, let's actually say that rect X should be equal to frame count times 2. And then frame, same for rect Y. And then get rid of this guy. And we're still going to want to mod that because as frame count goes up, it's going to go up infinitely. So we're still going to want to make sure it stays within range. Make sure that it still does the same thing. Cool, it does. But now we are doing it in terms of frame count. So that may not seem that special just yet, but hopefully in a few steps you'll understand why that's really useful. I'm going to also take out this println. One thing to know about printlns, you don't want to do it too much. We're trying to run draw over and over again as fast as possible. Printing stuff out to the console is kind of slow, so it will slow down your sketch. So if your sketch is running slowly, just make sure that you don't have any stray printlns in there. So now we have this explicit link, right? We can say at frame count X, the rectangle should be at some point P. That's time travel, really, right? That's cool. We now control the passage. In fact, if we were to, well, let's see, I think I might have missed one step here. Yes, I did miss one step. So we've got frame count in here. Let's actually move it out to a separate function. So rather than doing it inside of draw, let's have a new function that is draw rectangle, and we're going to pass in the frame count. Okay. So we've got this draw rect frame, and it takes in the frame. We'll call it frame number, just so you can tell that it's different. It's the thing that was passed in. We're going to move that here and here. Okay. I'm going to keep our clear up there. Cool. Now just real quick, what I've done, I've taken that same code that we had, just moved it into its own function, and we're passing in frame count rather than calling it directly. So now when I run it, it's doing the same thing. Okay. Now we could actually change this to be mouse X, right? It doesn't have to be frame number. We just need to pass in some frame number that with respect to our draw function here. Now if I do that, we can scrub across here and actually control the flow of time. Wow, okay, that's the time travel moment. I missed my big moment. So now we can control this because it's in a separate function that takes in the parameter that should control the flow of time. We can change what it's based on. So we could base it off a mouse, we could increment it manually. In practice, we're most of the time going to be using frame count to let processing run it magically. but we could have it based on something else. So it's self-contained, and we can tell it at which point in our animation it should go to. Cool. Okay, now time travel moment. Yes. We have full control over our loop. This is a powerful concept. We can now scroll through our animation, whereas we couldn't do that before. So we've solved the second question. We can actually know where our rectangle will be at a particular frame. But we still don't know how long it will take to complete. Again, that information is implicit. You know, we know that it's going to be traveling 2 frames or 2 pixels per second, or 2 pixels per frame rather, and the screen is 500 pixels across. So that means 500 pixels divided by 2 pixels is going to take 250 frames for this to run. But that's not built into our code. It's like, that's implicit. We had to figure that out. So how can we actually build that in? It would be nice if we could specify how long we want our loop to take. Like, let's say we want it just to take 2 seconds. Let's take a look at what code might do that for us. So we could pass in, let's say we want to pass in another parameter that's how many frames it should take. We said 250 is how long it's taking. We're just going to do 240 because it's a nice multiple of 60. So this should be 4 seconds, assuming that we're running at 60 frames per second. 60 times 4 is 240. So then we'll take in our total frames. Okay. So now we need to figure out something. We need to figure out, based on this frame number that was passed in and the total frames, how far along should we be in our animation? So we're going to take a look at 2 techniques here. We're going to use that modulo thing that we just talked about to calculate what our, actually I'm going to switch these to floats because we're going to be dealing with fractional numbers in a moment, and ints don't do fractions. This is another Java-ism. We have strong data types. Ints can only be integers. Floats can be decimal numbers. But so now we're going to take this frame number, and we want to make sure that it's always within total frames, right? Because frame count is going to be going up infinitely. It's going to go higher than 240 for sure if we let it run long enough. So we're going to want to make sure it's within range. So we're going to do that same modulo trick that we talked about to figure out what the current frame of our loop should be. So we'll take our frame number and modulo it by the total frames. Right? So that's how many frames into our animation we should be. So let's see what happens if we do that. We're passing in frame count here. What's it complaining about? Oh, matches with int. Oh, again, I said that these were ints before. Now we're going to make them floats. It's OK. And that error goes away. Cool. So hopefully when it gets to the end, cool, it's doing the same thing. Again, you're probably like, all of this code does the exact same thing. Why are we digging into this? We're building up a mechanism that will allow us to be really expressive in our loops, and that'll become apparent as we see what we can do with this expression, expressiveness. So right now, again, we're still dealing with this in terms of the current frame of the loop. But what would be a really useful way, like what if we just had a number that is from 0 to 1, and if it's at 0, we're at the beginning of the frame, and if it's at the beginning of the loop, and if we're at 1, it's the end of the loop. Anything in between is some fractional point. So we can actually, we're not restricted by the frame number. We just can, like, at any point on our timeline, we can figure out where we should be within our loop. Well, we have the loop frame. That's like what frame number of our animation we should be in. We've got the total number of frames. So if you think back to high school math or middle school math, I guess, if you divide the current loop frame divided by the total number of frames, that'll give us the distance across the total number of frames that we are. So let's do that. Let's call it normalized, because that's the term for this kind of value that runs from 0 to 1. Let's take the loop frame and divide it by the total number of frames for the loop. Total frames. And now, instead of using loop frame to determine where we are in our rectangle, or where our rectangle is located, let's use normalized time. So again, this value is from 0 to 1. So that means rather than caring how much we increment the rectangle by, right now we're incrementing it by 2 pixels per frame. But like, let's take this out for a second. What if we change this to be 120 frames per second? see, yeah, see now our loop is, it's still running, we're still incrementing 2 pixels per frame, but we're not getting all the way to the end. We only have 120 frames within which to work, so it's only going half the distance. And that's because right now we're focused on how far the rectangle moves for each frame. We don't, like, if we think about it, if we were to describe this loop to someone, we wouldn't say the rectangle is moving 2 pixels per frame. We actually would say it starts at the left and it goes to the bottom right. So what if we can structure our code in a way that allows us to write it the same way I just described it, right? We don't want to care that it takes 2 pixels per frame. We actually want to say at the end of the normalized time, like at the end of the loop, we want it to be at the end, the far right edge of the screen, and at the far bottom of the screen. In fact, we don't even need this mod stuff anymore, because now we have this normalized time value that's running from 0 to 1, and based on that, we can tell it, the rectangle, where it should be. So I'm going to put this back up to 240. Again, we have the exact same animation, but now if I change this number, it actually does affect, it's the same motion, but it goes faster, right? So that's really what we care about. We care about the actual motion, not about the individual steps involved in that motion. So this is extremely powerful, right? Because now in these 2 numbers, we can say how long should our animation take with the normalized time and with the frame total frame count. So that's really cool. We're going to take it one step further, actually, because now if we look at this, this is the code that's responsible for drawing our rectangle. Actually, these things here. But this stuff, I mean, where we're doing this math, this doesn't actually have anything to do with what we're drawing. We just want this normalized time number. So we're going to pull this actually out into a separate function. Right? We're going to have, let's say our draw rect, just all it takes in is a normalized time value. That's all we care about. From 0 to 1, how far is our loop? And then we'll take this stuff and put it into a separate function that we'll call our loop normal, right? Because we're going to be generating a normalized value based on the current frame number and the total number of frames. Just return this actually. Cool. So that means up here, we're going to first want to call our normalized time. Or save it into a variable called normalized time. We're going to call loop normal and pass in this frame count and the number of frames that we want it to take. And that's going to give us our normalized value. And now we can pass that normalized value into our new draw rect. Normalized time. Cool. So now we've split out the concerns, right? We've got, I'm going to move this after this actually. We split out our concerns. We've got our drawing concerns. All this thing cares about is how far through the loop are we? And then based on how far we are, where should the rectangle be? This is responsible for maintaining the structure of our time. This is our time travel loop, or time travel function. So now if we run this, cool, it's the exact same thing. Can we make our processing window wider? For sure. That's good. Yeah, good point. It's going off the side. Thanks for calling that out. Yeah, so this is really powerful, right? It seems like we've been doing a lot of work just to get the same thing over and over again, but this is an extremely expressive way to control our loops. And we're going to be using this function for the rest of the course. I use a version of this in every single animated GIF that I've ever worked on. I think in any environment where you're going to be want type control over the way passage flows in your application, you're going to do some version of this. Cool, so that was a lot. Let's go back to the slides and see how we're doing.
Someone asked for you to make the processing window wider.
Yep, I saw that and I did.
Okay, cool.
So hopefully you can see everything now. Thanks for calling that out. Cool, so we did this, we can now actually specify how long our loop should take to complete. That's just one number that we pass into our normalized loop. We pass in 120, that means it's going to take 120 frames to complete. So now we've answered all of these questions, which means we're prepared to take control of our looping destiny. So just a quick note on normalized values, and we covered this a little bit. They're values that run from 0 to 1. It took me a while to understand why everyone is so obsessed with normalized values. I would see people's code and be like, wow, there's a lot of things that just run from 0 to 1. They're extremely expressive. They're really useful for taking ranges of values and comparing them to each other and mapping them to each other. Like in this case, we don't have to deal with the number of frames. Right? Our frames happen to run from 0 to 120. But if we just drop that into 0 to 1, we can apply it to all sorts of other things just by multiplying it. Right? We wanted at the time 0 for the x-coordinate to be 0, and we wanted at time 1 for the x-coordinate of the rect to be 500. So we can just multiply them together. It's really useful. They're your best friend. We're going to be using them a lot throughout this workshop. We're doing things like color, position mapping, angles. See, I might have gotten ahead of myself and said, can we make, yep, I think I did. I jumped ahead. So this, yeah, the question here was, can we make draw rect simpler? Because it was taking in the frame count and the total number of frames. In spoiler, yes, we already did it. The spoilers happened even before I gave you the spoiler alert. So yeah, if you were to click on this link, it would take you to the code that we just wrote. Cool, I get excited. All right. Cool, so that was a lot. I think now would be a good time to probably do a breakout room. I think we're gonna break out into groups of 3. Do it for about 10 minutes and maybe say hey to each other, talk about how things are going, try and play around with some of the techniques that we've just played with. Feel free to please at this point click into those sample code if you're not caught up, so you can just take that sample code and have the loop normal to play with. Yeah, and I will also put that code on the screen during the breakout session. But again, if you want to go and to the website here, I'm just going to call that out again. If you go to the code samples link here, even if you're not following on the live slides, you can go to the code samples. All the code samples are going to be there. And if you're following on the live slides, you should be able to click.
Do you want me to set, so there's settings where I could automatically close the breakout rooms after a certain amount of time? Do you want me to do that?
Sure, yeah, let's stay 10 minutes just to keep us moving, because we do have a lot of content. I can see at my quick time check. Okay. I'm already a little, well, actually I'm doing pretty well. Okay.
Okay, yeah, so 10 is
10
enough?
I think so. Well, I can see. Let's ask the audience. Does 10 minutes feel like it's going to be a good session? You want to do 10 or 15 minutes?
For what's their goal?
The goal, I think, is to just review some of the content that we've gone over here. So take this code and play around with it. Make sure that I'm not just talking code at you. Like try and get some hands-on experience with drawing rectangles, playing with the loop normal.
Okay. All right, that's fine. I'm just gonna, once I do it, it's done. Okay.
Yeah, let's do 10 minutes and then we'll come back. And then we'll find out how it went.
And if you get thrown into a room, you can always come back to the main room, by the way. So I hope you won't, but we'll see. Why are these rooms not working?
Is it not working?
It's weird. It's not working. It's just, I said to automatically assign it, but it's not working. Hold on. Recreate, automatically assign, recreate. Okay, here we go. Open all rooms. I think it's because I did it before everyone was here.
Hello?
Did you get into a breakout room?
I did, but the person wasn't saying or chatting or
Just
anything.
being weird.
Yeah, it was just silent. So
Great. Well, here you are.
yeah. Just wait for it to end.
Yeah, I'm not quite sure how that was. Whatever, it's fine. It'll be over in like 5 minutes.
Yeah.
Did you
it's okay.
understand his lesson, or do you need
Yeah,
help?
I totally get it.
Oh, cool.
So yeah, it's really interesting.
Okay,
I'm
good.
actually learning Houdini, and it's pretty great to think about how I can use some of the things I'm learning here to apply to that.
Houdini's like 3D, right?
Yeah. Yeah.
I've heard. I know, like my friend Shelly was into it, and then I only used Unity, and I've done more low poly, like Blender. I kind of can use, but
yeah,
I'm like better at coding, and but I like want to learn. Like I'm very impressed, and end up having to do a lot of work with other artists, like for shows we do that do better, way better 3D than me, and putting them into 3D spaces. And so working with the files and the textures. But I find that I've had a lot of trouble. Like I know I can make a shader because I can code variables, but I can't. I have trouble like understanding all of the million settings to make materials and apply the shaders, and then like transfer them between 3JS and Blender and a million kinds of like. There's so many file types for 3D too, and they're all like. Some of them put the data. I don't even know. It's been a huge learning curve, but
it is.
It's a lot. Like, and there's like Cinema 4D, there's Houdini, there's Unity, there's Blender, there's Maya, we had a data viz class yesterday, and just the sheer amount of software platforms for doing data stuff that she just covered. I was like, oh my God, so many things. And they're all kind of similar, but not, you know what I mean? But they all have things they do better than each other.
Yeah, and it's evolving really quickly, and like I think Unreal has kind of like that demo.
Oh God, I forgot about that. Yeah.
Yeah, that the demo they released kind of wowed everyone, and so everyone's getting behind Unreal to use as like as a method to render some of the things you make in other apps. So yeah, it's really fast moving.
I know. And the guy, what was the one he was? God, I can't even remember. We did. I don't know. Are you local here?
Mm-hmm.
Did you see the end of you show we did?
No, I didn't.
Yeah, because there was like a whole projection mapped. We used most of the oh my God, the cine chamber, but we also projection mapped on the floor, and
oh, cool.
Did a bunch of projection, crazy, and also tracking with the camera. But the rendering time that we had, like for a lot of the pieces, was a whole other, like, and paying for the servers to do the render, like all of these. I didn't even understand that was a thing until doing this like larger scale.
Oh yeah.
So it's just crazy.
That's why Unreal is so appealing, is it skips all of that render time pain,
Yes.
So yeah, it's pretty exciting.
Yeah, that is great. But my point was that the biggest part of the exhibit we had was done with Unreal, and then in Touch Designer as well.
Oh yeah,
with the interaction, and then we were moving from it anyway. But I would like to learn more, and I have to learn it for my job to some extent. But I still feel like there's at least with the shaders, textures, and importing materials between softwares and then putting them into 3JS is like a barrier to entry that I still have not. Like I can make something looking cool in Blender, and then I'm like, Anna will stay there forever because I have no idea how to get it out of Blender.
Yeah.
Into anything else. And when I made a VR game, and I ended up just using all like other assets I did not make, because I was like, I don't know I cannot for whatever reason, like I can write like a flocking script, but I can't I can't make like a texture apply to an object. I don't know what is wrong with me, but I guess people they study 3D graphic, right? Like there's like a whole degrees for that. But
Yeah.
I've just had so much trouble, like, and then also I'm always like, what's the cutting edge web technology that's broken? And that's the one I'm using, you know? It's like,
Oh man, yeah.
yeah, because I'm a JavaScript nerd, so I'm like, oh, I'll do it in JavaScript and it won't work. But if you
Yeah.
just do it in Unreal, it probably would, or Houdini, it would work really well. There's some cool art coming out of Houdini and Cinema 4D as well. Like
Cinema 4D is really
Morphe
cool.
stuff.
I really want to play with it, but it's expensive.
Oh yeah, I don't know how much it even costs.
Which is it?
Cinema
4D, you
4D?
mean?
Oh yeah, it's very pricey. Yeah.
You know, sometimes though you can beg them. I often get a lot of free software through Gray Area for artists who are in our
Oh,
incubator
that's cool.
or who are doing projects with us, by just writing letters of sadness. Like, help! We need these licenses.
Can I reference Gray Area and ask for a Cinema 4D
Yeah,
license?
I don't mind. Sure, just say you need it and teach a workshop for us.
Awesome.
That
I'll
sounds
write
great.
you
Yeah.
a letter. What's called a letter of support. It'd be like, as a festival instructor, I support this person in getting a license. So that's all you need.
That sounds awesome. Thank you.
But some companies like Sweetwater was really sweet about it, ironically, for us to get a lot of processing and software, but not, it just depends on the company. Some of them like won't give anything away. Mad Mapper will kind of give you a discount, but
Actually, I got Mad Mapper when I was teaching in Berlin. They were okay with
free.
It was significantly discounted.
Yeah, it's not free.
It was not free, but it was
They'll
definitely.
just, a lot of places will just straight up send you licenses for free, like many of them.
Wow.
So anyway, it always hurt. It doesn't, everyone listening to this, it never hurts to beg a software company and say you're an artist and like send them your portfolio and be like, can I get this for free? It's the pandemic. They might give it to you. That's all.
Cool. We're all back in the main room now?
Back.
Cool. Well, hopefully people found that useful. I found it useful. I got some feedback that this last part where I pulled out the loop normal frame number total frame stuff was a little bit confusing. And again, that's partially my fault. I kind of jumped ahead of the slides and just started coding. So real quick, I want to see if this will work. Oh man. Beautiful. Okay, so now I'm going to switch over to my overhead projector. And I'm going to try and draw an illustration that might explain, hopefully help explain what just happened, right? So I write kind of small, so please call out if you can't read this. But you can imagine, like, what's processing gives us from the start is a frame count. And that is always increasing, just forever, goes on into infinity. Can everyone read that?
Yeah.
Yes.
Yes.
Cool. Awesome. And then, so that frame count is always increasing. And what we did was we chopped that up into loops, right? We said that we wanted to take, I think, what did we say, 120? So every 120 frames, we want to start the loop over. So we're basically chunking that up. So this is 120 frame loop. This is 120 frame loop, 120 frame loop. And we got that by doing the loop frame is equal to the frame count. My handwriting gets atrocious when I write big. Modulo the total number of frames, right? So total frames was a number that we specified, which is how many frames we wanted it to be, 120. And then the current loop frame is basically how far across the duration of our loop should we be in frames, right? So if frame count is 180, we're right here. But our loop frame, because we've started over, should be halfway through our loop, which is 60, right? So that's what this expression is going to get us. Then we wanted to take it one step further and change that from a frame number to a number from 0 to 1. And I want to show 3 different graphs of why that's a useful way to express it. So here we have the loop frame, which we just calculated there. So it's running from 0 to total frames, in our case, 120. And if we were to normalize that, basically we want the exact same range, but running from 0 to 1. That's really hard. That says normalized, running from 0 to 1. So if we're halfway through our total frames, we're at frame 60, we just want a normalized value of 0.5, right? So this is a really succinct way to express how far through our loop we are. And that's really advantageous because then we can map it onto aspects of our drawing. So in our case, we wanted X and Y to map from 0 all the way to width. And we can do that. It's a straight mapping. Because over here, if we multiply 1 by width, it gets us where we are. If we take 0 times width, it gets 0. And if we 0.5 times width, it's halfway through the width. So that's why normalized values are really useful and why it's expressive to talk rather in terms of frame number, in terms of the normalized value of how far through our animation we are. Because then we can, as we saw, we can change the total number of frames to make the animation run faster or slower. None of our code has to change because the code only cares about the value from 0 to 1. We're just changing how fast that number goes from 0 to 1. Cool. So yeah, that's my little drawing. I hope that helps explain a little bit what happened just in that portion. Maybe I'll take, actually, definitely after this, I'm going to take this drawing and make a version of it that fits into the slides just to reiterate that fact. Cool. So I'm going to jump back to this camera here. Yes. All right, and I'm also going to share my screen again. Ah, cool, Winston, thanks. I'm glad that helped. And yes, Christina mentioned printing. Printing does really help. Just use printlins to get a sense of how values are changing over time. It really helps you kind of cement what's going on there. All right, let's see if we go back to the slides. Hopefully I'm still logged in. Neat. Cool. So with that loop normal function, we're very close to unlocking the secret of the loop. So we've been focused on creating a timeline that we can scrub from 0 to 1. And the secret of the loop really is to end where you started. So it's to have at time equals 0, your frame look exactly like it did at time, or does at time equals 1. Because then when you start over, the loop is seamless. And there's a lot of different ways that you can achieve that. We saw, in our opening with the examples, we saw cinemagraphs do it by kind of clever blending. But there are some mathematical ways that we're going to take a look at. And my favorite way to look at this is trigonometry. This is probably the first time you've seen this word with an exclamation point. And the picture is here mostly as a joke. It actually is a quite expressive picture. It's very informative, but it's going to be a lot simpler than it looks. And I think if trigonometry were taught this way in high school, I would have found it a lot more exciting. So we're going to take a look at these three trigonometric functions. Actually, most of the time we're going to be spending on sine. And so just to refresh what trigonometric functions are, I'm going to take a look at this graph of them. This is a really useful tool, by the way, desmos.com. It's a crazy powerful graphing calculator. Like you can write anything here and it will render it. It's pretty cool. So what we have here is the sine of x. So we've got our x and y coordinates here, back in the familiar bottom left 0, 0 land. I'm going to turn these off. We're going to look at the sine, right? So sine is just a repeating wave like this. It means as we increase, we have this x that's going forward, forward, forward into infinity, which sounds a lot like our frame loop number, actually. That might come in handy. And as that number goes up, if we feed it into this sine function, it's going to give us something back that repeats. That seems kind of cool. That seems like it might be really useful for looping. Cosine basically is the same as sines, just shifted over a little bit. We'll take a look at how they're defined if you want to understand why they look that way. Tangent also repeats. It's a little weird. It goes from negative infinity to positive infinity. It's a little bit less useful. Right? Like I said, we're going to spend most of our time on sine. But it can be useful. I use tan for this animation that I did. This animation is actually called tan fall because it uses the tangent function to coordinate the positions of these cubes. So they just fall down to infinity and they come back from infinity, and it's kind of a neat effect. But let's focus on sine wave. So let's first take a look at this visualization of a sine wave. This is a textbook on all kinds of things for digital signal processing, but it's amazing. It's got all these interactive graphs. This is a really cool way to look at what is a sine wave. A sine wave is actually, if you go around a circle at a regular frequency, so it's this frequency here, a sine wave is the y coordinate. So you see, as this point on the circle, the y coordinate is going up and then down. And cosine is just the x coordinate. So that might come in handy a little bit later too. This is just a really cool way to visualize that. And then we can control the amplitude, which is how big of a circle and how tall of a wave we generate. I also have this demo sketch that I put together. These demo sketches are not available right now on the code samples. I had ran into some trouble with external assets, but I will post them. They will be available to you after the workshop once I figure that out. But if we go back into processing and we open up, let's go to the area to Design Explorer. This is one of the cool things about processing is you can use it to create interactive learning tools. So this is basically the same thing that we saw, but it's responding to my mouse. So you can see as I move the mouse, what the relationship on the sine wave is to the position on the circle. As you can see that this green dot maps to the green line here. Basically the exact same visualization that you saw on the website, but it's interactive, which is cool. So what are some facts about sine waves? Well, we noticed that they repeat. In fact, they repeat every 2 pi. We take a look at the trigonometric functions here. We see we start at 0. The next time that it gets back to 0 to repeat the same thing, it's around 6.28 approximately. Pi is 3.14. 3.14 times 2 is 6.28. So that's right there. So every 2 pi, it's going to repeat. And the range by default is from 0 to 1. That means at the top, again, at the top here, this is 1 and this is -1. I said 0 to 1, didn't I? -1 to 1. And then there's this graph that we can take a look at, or this equation that describes how the sine wave behaves. And again, you learned this probably in middle school or high school, but it is actually really exciting and applicable in code. And we're going to take a look at the graph again on Desmos that shows how those numbers relate to each other. So this is the simpler version that we're going to be using in code. If you want to make a sine wave bigger, you multiply it by a number. So sine wave by default is -1 to 1, but if you want to make it bigger, increase that a number, a value. If you want to make it more frequent, you increase the b number there, the thing multiplied by x inside of the sign. And if you want to shift it, which is something we're going to be doing a lot, you just add some number c to offset it. So that can actually make an animated wave. That sounds like kind of a cool idea. So we just saw that on the graph there. What if we actually draw this in processing using the sine function? Let's do it. So for this one, I'm going to keep around our loop normal, but I'm going to take out our draw rect. I'm going to change this to a draw sine. And actually, we're not going to use our normalized time for this just yet. I won't get ahead of myself this time. So it's giving me this error that I'm not using that value, but that's okay. I know it's not being used. So we're going to draw the sine function. So how do we want to do that? Well, we want to start at some base level, y, right? So let's actually center it on the screen, right? So let's start with a base value of y. That's the height times 5. That's going to center it on the screen. And just to prove that, let's draw a circle at 0 for x and base y, and give it a diameter of 100. Cool. So you see now we've got the circle, but it's centered on the y-axis. So we're going to use that as our starting point. And let's just, what we want to draw is a wave that goes across the screen. So let's start at x equals 0 and just go all the way across. For every pixel, let's draw the value of sine at that point. So we start with x equals 0, go all the way across the entire screen, incrementing by 1. And then we're going to take to figure out what the y value is by setting it equal to sine of x. Cool. And then let's just draw a point. A point is a special, it's a circle that's only 1 pixel in processing. We're going to draw it at our x coordinate here. And we could take our y, but we're going to add it back to the base y. So that way we're starting from the center of the screen and then going up or down from there. And you'll see what that looks like. Well, we don't see anything. Oh, part of that is because points by default are black and our background is black. So let's actually change the stroke color to white. So there's a sine wave. It's very small. Why is it so small? Well, because we said it's repeating every 2 pi, which means every 6 pixels or so it's repeating. So yeah, if you go 6 pixels, you can actually see the total, the full cycle of the sine wave here. That's not super useful. Let's actually, and it's also really small. We said the amplitude is only 1 pixel, so it's only going up 1 pixel and down 1 pixel. So let's first fix that with that amplitude that we looked at. We can multiply some amplitude by the sine wave. Let's set that equal to 100. That seems like a nicer value. Okay, now that's interesting, but it's it's cycling so fast that it doesn't even read as a sine wave right now. So let's decrease the frequency. Again, we saw that we can multiply the x value by some number to decrease the frequency. All right, now we have a sine wave. You can actually see. For x equals 0, that's the value of sine wave. X equals 1, that's the value, and so on. So we get this nice pleasing curve. Now we've drawn a sine wave just by iterating over all of the pixels across the screen, using the sine function on that pixel value, multiplying it by an amplitude to make sure it's tall enough to see, and decreasing the frequency by multiplying it by a fraction. Cool. So that's a sine wave, but we said we want to do loops, right? So let's see if we can incorporate the loop normal to take that sine wave and animate it. If we go back here, we've got this normalized time, we're not using it. So let's pass the normalized time into our sine wave function. Take in called normalized, right? Actually, from now on, I'm just going to call this t for time. That's usually what I use it in code. It's so frequent. Let's just call it t. And just know that t is always from 0 to 1. And let's see, let's think about what we actually want to change, right? So we want our sine wave here over time to shift. And if we remember looking at this trigonometric functions, sorry, this one, there's that one. That's fine. If we wanted the sine wave to shift, we need to add some value to the thing that we pass into sine, right? So if we pass in some value c, it's going to shift it over. So let's just try that real quick. Go back to processing. And let's just add some number 3, right? So right now, just before I rerun this, keep in mind that the loop starts here and then it goes down at the beginning of the screen. We're shifting forward by 3. Yep. So now we actually jumped a half cycle. Now it's going up. So that's probably the number. If we were to change this number over time, we would end up with a sine wave that moves. Yeah. And so that's what t does. T is changing over time. So t changes from the value 0 to 1. And we want our animation, well, let's try just adding that. Let's add t. See what that does. So we're adding 1, cool. So it's looping, but it's got that jerk. It's not a seamless loop, right? So it is actually getting this the animation that we want, but it's not running a full cycle of the sine wave. Remember, we said a full cycle happens every 2 pi. Right now, we're only moving across the loop, we're only moving a distance of at most 1. But if we multiply that by 2 pi, that means when t is 0, it's going to be 0. When t is 1, it's going to be 2 pi. And throughout, we're going to be moving smoothly from 0 to 2 pi. Hey, now we've got a seamless loop. This is our first seamless loop. The workshop lives up to its name. So, yeah, that's pretty cool. This is actually, it turns out that, let's switch back to the slides. It turns out that just with that, you can make cool art. So actually, this is one of my first pieces that I did, I think, during COVID. And it's just a bunch of sine waves, right? And they're just animating across the screen. And all I've done is alter the relative wavelengths and colors of them and done some cool blending effects, which we will take a look at later. But that's all it is, it's a sine wave. So that's a really good starting point for making some art. Cool, so I'm gonna take a quick pause and check the chat to see if there's any questions so far. If anyone has any feedback on how things are going, let me know. I'm gonna drink some water.
Can we have a quick review of loop normal?
Sure, yeah, so loop normal, again, it's basically our playhead. We pass in some value of total number of frames, which is how long we want our loop to run. And then we pass in the current frame count. And it's going to figure out, based on the current frame count, like how far along processing is run, how far should our loop go from 0 to 1. When we call this, we're going to get back some number, and that's going to be our playhead moving through our loop. When I say playhead, like the thing at the bottom of a YouTube video that's scrubber. So that's how you can think of this function. You just call it, you get back a number, and then you pass that number into your function, and it becomes the thing that controls how your animation runs.
And the return is just returning the value. The line return is just.
Yep. So that takes this. When you call this function, it's going to return this value, and we're saving that return value into this variable and passing it into draw sign.
Okay, perfect. Thank you.
Yep, for sure. Cool. So time check. Let's see how we're doing. We've got hour and okay, so we're a little bit behind. So we've got this sine wave. We can draw waves, but can we use it for other stuff? Turns out yes. Otherwise, why would I ask that question? We can use it to modulate other parameters on on our shapes. So if we wanted to, let's do a coding exercise where we're drawing a circle, but we want its shape, its size to change over time based on sine waves. So I'm going to change our name again. So we're not drawing a sign anymore, we're drawing a circle. And let's say we want our circle, so I'm just going to get rid of everything that we have here so far, start from scratch. We want our circle to be centered on the screen. So first we need to figure out how to get the center. We can do that by taking the width and multiplying by half. And doing the same thing with the height, multiplying by half. Ooh. Okay, let's just start with that. Let's draw a circle at X center and Y center. And let's put our diameter into a value too. So let's say it's 200. Seems like a good number. Oop, I'm not using that, so let's use that. Cool, and if we run that, yeah, we've got a circle of diameter 200 pixels from side to side. Cool, but it's not moving. So what we want to do is we want to change this value over time. We know we actually want to do it based on a sine wave. So if you think about it in terms of the sine, well, let's try and see what happens when we take the sine wave of t, and then we had to multiply by 2 pi. So this means that as we run through our loop, t is running from 0 to 1. Our sine wave is running from, or our input to sine is running from 0 to 2 pi, which means that this is going to run a full cycle down and up. What if we use that for our diameter? Well, we're back in the situation that we were before, where it's drawing it, but again, sine only returns values from -1 to 1. So we're seeing a 1 pixel circle getting drawn there that's so small we can't even see it. So if we multiply it, again, earlier we saw that if you multiply sine by some amplitude, you get a larger number, or you get a larger waveform. So let's multiply it by that number that we had, 200. Hey, look at that. We've got a seamlessly looping GIF, or a seamlessly looping loop. It's not a GIF yet. And it's animating the size of this circle. It's not looking quite right, because a sine wave should slow down at the top and bottom, which it seems like it's only slowing down at the top. Well, let's go back to our slides and see what's up with that. Something doesn't seem quite right. That's because, like I said, the sine wave is returning values from -1 to 1. So it means that sometimes our diameter is actually going down to -200. So take the advice we saw earlier. Let's try and print out this diameter to see how it's changing over time. You see it going up to 200, and then we're getting down to these negative numbers. So we're actually passing through 0 really quickly. And it just happens that if you pass a negative number to circle, it's smart enough to figure out that you probably don't want a negative diameter, you want a positive diameter. So is there some way that we can take the values from sine and map it to some other values that we want for our diameter? It turns out we do. We have a mapping function in processing. It's built in. So it's this map function. If you take a look at the documentation, it'll talk you through how it works. It takes in some value, and we're telling the function, we know that this value is going to run from some start across some range, start 1 to stop 1. So in our case, we're going to have a sine. We know it runs from -1 to +1. And it will map that value onto some other range. Similar to those 3 timelines that I drew earlier in the notebook. It's going to take the values, this value from one range and map it smoothly over to a different range. So I've got a demo sketch that will hopefully illustrate that. Let's take a look. Cool, so this is just like the thing I drew in the notebook. You see that on the top here, we are mapping, we're showing the value of mouse X. So this whole screen this whole window is 1,000 pixels wide. So mouse X is wherever I am from 0 over here to 1,000 over here. Down here, what we're seeing is the value of mapping mouse X from 0 to width, because we know that mouse X is running from 0 to width. But we want the new range to be 20 to 50. So you can see now when mouse X is 0, this value is 20. And it's returning a decimal number that smoothly interpolates all the way up to 50. So we can actually take one input of ranges and map it to a different range as our output. So that's exactly what we want to do. We want to take the input of sine from -1 to 1, map it to some output that's a reasonable set of range of values for the diameter of our circle. So let's try using that. Let's try using map. We're going to take this map function, and we know that sine, again, we said it expects 5 numbers. The first one is the value, which is going to be our sine function. We're going to, the second and third are the beginning and ends of the range, which we know are -1 and 1. Now we get to pick what number we want this to be. So let's say we want, at the smallest point, our circle should be 30. And at the tallest, let's say it's, well, let's see, our whole screen is 500. So let's make it take up the full screen. We'll print that diameter out so we can see how it changes over time. So now we've taken that sine wave, that sine motion, you can see it in the characteristic of how this shape changes, but we've changed the values that it's constrained to. You know, when the sine wave is at its highest point, we're making the circle the width of the full screen, 500 pixels, but when the sine wave is at its lowest point of -1, we're no longer going into negative numbers, we're just going down to 30. You can see it past there, 30. And take out those print lines, because again, it does make things slow. But so now we've taken the sine and we can map it onto an aspect of our shape. And we could change it. We could make it an ellipse even, which is a special circle that has a width and a height. And let's just say that it's always 500 pixels tall, and we're only changing the diameter. Now we've got this like spinning coin effect, right? But we're just changing the width of the ellipse and not the height. So this is a really powerful tool, right? Because we can take the output of our sine, map it to some new values that are appropriate for whatever it is we want to do. Right now we're playing with width and height, but we could play with position, we could play with color. And yeah, looks like I've already jumped ahead. So we drew a circle whose diameter was modulated by sine from 100 to 30. I was doing from 30 to 500, but you get the idea. Cool. I had, again, I've pushed out a little bit the breakout times. So I want to, just in the interest of time, we're going to push this one out a little bit further. But I do want to recap what we've covered so far, right? Because we've got some three really powerful concepts that we've derived here. We've got our loop normal function. It controls our loop's length and its playback. And the playback comes in the form of a value from 0 to 1. And we pass that value into our loop, our drawing function and use that to dictate how far along our loop should move. And we've got our sine function, which we can use to modulate parameters of other shapes. We saw that we can we can generate a wave, and then we can alter it using by multiplying it to increase the amplitude, or adding a value to make it move. Or we can just take the output of the sine and map it to some other range that's more useful for us. And I think this is a little bit clearer way of expressing what you mean, rather than multiplying and adding things. Just do map. You know that you have a sine wave that runs from -1 to 1. You can map it to some new range. So let's take a look at another secret of the loop. You know, one way was to have a function that always repeats for us. But another way to do it would be to fake infinite movement. So we could take like a bunch of repeating objects and move them such that it appears that they move into the next place. What do I mean by that? Let's take a look. Look at this loop. It's 4 circles that are rotating infinitely. You've probably seen something like it if you've ever seen a web page load. But the cool thing about this loop is the actual frames that construct it they only construct a quarter turn. Because if you follow this dot from the left, when it gets up to the top, that frame looks exactly like it did at the beginning. So just by illustrating only a quarter of the turn, we can actually end up with this infinite illusion of it turning forever. This was another example I saw. There were several big tech companies that went public in the past week, and all of the articles referenced this same GIF, which must be from some like GIF library somewhere. They had this as a header image, and I thought, wow, this is a really good example. So I brought it in. It repeats every time the lines hit the edge. So it gives us this illusion of infinitely moving up and to the right. But it's really just enough frames to move the squares over and down one row and one column. I realized, well, actually, we could probably pretty quickly make that. So let's give it a shot. Let's draw a grid of lines that move endlessly to the bottom left. So for this, we're going to, again, just clear out everything that we have so far. We're going to keep our loop normal because that's our playback. We're going to keep our t, which is 0 to 1. That controls the playback. We're not drawing circles anymore. We're drawing a grid. So, well, if we're drawing a grid, we probably need to decide what we need to know to draw a grid. We need to draw how many rows and columns it is. So let's just come up with some rows. Say it's 10 rows. Let's do the columns. Let's just make it a square grid. So columns are the same number as rows. Cool. And then how far apart should these be? We want to split them evenly across the screen. So we can do that by, this is going to be the distance between the lines in the grid. We'll take the width of the screen and divide it by rows. Right? So we have 10 rows and we want to distribute them evenly across the screen. That's how we would do it. Cool. So now how would we draw the grid? Okay, we know how many rows and how many columns there are. Well, we just want to draw some lines. So we draw a set of vertical lines and a set of horizontal lines. So let's start with the vertical lines. Yeah, let's start with the vertical lines. So we'll just create some for loop. And for each of the columns, we'll start I less than columns. Right, so now we're going to iterate through those. And how do we know where we want to draw them? So we're going to have some x value for how far horizontally across the screen are we drawing. Well, let's see. We have the distance, right? So this is the distance between each line. So that means we would want to draw I times the distance, I think. Right? So if I is 0, then we're going to be drawing at x equals 0. If I is 1, that's going to be the first line, and we're going to have jumped a distance of distance pixels to the next line, and then eventually we'll have drawn column number 10 columns across the screen. So let's just try that. Let's draw a line. And the way the line works is it takes the point xy of the starting point. So we're going to start at x coordinate, and we're going to start at y equals 0, which is the top of the screen, remember. And then we're going to keep it a vertical line, so the x is going to be exactly the same on the top and bottom, but the y value here is going to be height. Okay? So let's see what that does. Oh, again, we're defaulting to drawing black, so I'm going to draw our lines white. Look at that, we've got some grid lines, vertical grid lines. We want to do the same thing for horizontal, which is going to be a very similar bit of code. So just copy and paste that. But instead of columns, it's going to be rows. Instead of x, it's going to be y. And here, this is going to change. So let's start over here. For this, we're going to be drawing from the left side of the screen to the right side of the screen. So the left side of the screen, the x-coordinate is 0. Our y-coordinate is how far down the screen we are, which we're figuring out within this loop. And then you want the line to go to the other side of the screen with y. So that's going to end up drawing a bunch of horizontal lines. Let's take a look at that. All right, we've got a grid. One thing just to make this look a little bit nicer, I'm going to make the stroke weight thicker. So the stroke weight determines how wide is the stroke. So now instead of 1 pixel, we've got 2 pixels. So it just looks a little bit nicer to my eye. Cool. So, but now we want to make it move. Okay. So now we've got our base set up here. This is kind of the structure I do for all of the animations, right? You figure out what your base structure is, how to draw that, and then how do you want it, once you figure that out, how do you apply movement to it using this G value? So we know that we want the lines to move, appear to move to the left and to the bottom. So let's focus on one dimension at a time. Let's say we want to move the x value. So the way that we're going to do that is by changing this x value here, right? By default, we've got this base value of where they should start. But then we want to add some value to it, or change some value. So like if we take x and we say it equals to, let's just use t. Again, let's start off with just t. So that means as our loop runs, all of these x values are going to increment by 1 pixel. We run that. No, it's so subtle you can't even see it, I think. It's moving to the right, I think, by 1 pixel. Okay. So that means 1 pixel is probably not enough. Let's actually multiply this, because again, we can increase the amplitude of our time. We actually want it to move distance pixels, right? Because if we move it to a distance of distance pixels, that means it's by the time the loop ends, the lines are going to have moved to where the previous lines were. Right, so look at that. Now the loop is actually starting over when you see this line appear over here, but it looks seamless because throughout the duration of the loop, our x value is moving until it's exactly where the previous line was at the beginning of the loop. Right? So we've got this illusion of it moving, even though it's really just the lines are moving and then it's jumping back. But it's going to the right. We actually wanted it to go to the left. So let's actually, instead of adding, let's subtract, change the sign. Cool. Okay, now we've got it moving to the other way. Well, we can see the illusion. The illusion breaks down. So it's moving to the left, but we don't have an extra line over here to move in. That's because we're stopping at the very edge of the screen. If we do this instead of less than calls, we do less than and equals. That means we're going to add one extra iteration of the loop, which will put one extra line on the right. Cool. Now we've got this infinitely looping grid that moves to the left. We want to apply the same logic to make it move down. So we're going to be adjusting the y value. In this case, it's going to be adding that same value, so t times distance. All right, we've just recreated that animated GIF. In fact, if we want to complete the illusion, we could go up here. So this is our main draw function again. We're drawing something based on time, but then let's just draw a circle on top of it. Let's draw it at the center. And just give it a diameter of 200. Look at that. We've created the same illusion. We've got this circle that doesn't move, right? Because every time we run through this draw loop, it's stationary. Nothing about it is affected by time. But we've got this grid that's drawn underneath it that appears to move. So I think that's pretty cool. And it wasn't a lot of code to actually get us something that we saw on a professional news site. So let us jump back into the code, or into the slides rather. Let's look at another example of this. This is the example I was using previously before I saw that news example. Let's draw a grid of circles that moves down endlessly. So in that case, we're going to use some very similar code. Jump back into processing. We want to draw a matrix of circles. Matrix is just a fancy thing for a thing with rows and columns. This is what we just drew with this grid lines. And we're going to want to run through, let's keep it the same. We're going to have some number of rows and some number of columns. Instead of distance, it's going to be the diameter, right? Because the circles are going to take up that whole distance there. Let's get rid of what we have here. Oops. And right now we have these two separate loops. We're actually going to want to run a loop within a loop, right? Because we're going to first want to run through all of the columns. And then for each column, we're going to create a circle for each of the rows. So let's actually put this loop inside. We can't reuse the same variable names. I'm going to change that to j. Okay. Okay, so now what's the logic here? We're going to run through each of our columns, meaning we're going to run across the screen from left to right. If we're moving from left to right, that means we're dealing with the x coordinate. So we're going to figure out the x coordinate. And let's just say it's, again, the same logic that we used for our grid lines, I times diameter, in this case, instead of distance. And then same thing for the y values. We're going to do j times diameter. And let's just draw that. Let's draw a circle at x and y, the diameter of diameter. Oh, we still got, that looked kind of cool, actually. What happened there? We've got all of our circles, and then we've got another circle on top of it, but the edges kind of blur together, so you get this neat effect. See, this is what I mean. I didn't mean for that to happen at all, but it's kind of cool. Processing is really fun that way. So I'm going to get rid of that circle on top. We're going to change this name. We're not drawing grids anymore. We're drawing circles. The names don't matter as long as they match up, but I just want it to be expressive. Cool, so we're drawing the grid of circles. It looks not quite right because the x, y value that we're giving are actually the center of the circle. So it's a little bit offset. So actually, let's go and for each x and y value, we actually want to push it over by half the diameter, right? We want to shift it over by the radius of the circle. So for each of these, let's add half of the diameter. Cool, now we've got a bigger circle. But we want it to move down infinitely, okay? So moving down, that means we're going to start to incorporate our time value, the time value t. Just going to clean this up a little bit. And we're going to want to move it down, which means we're going to be playing with the y coordinate. So let's change the y value like we did before. Let's say head in, again, we'll start with t. Yep, it's moving, but it's moving so subtly because it's moving by 1 pixel. We actually want to multiply again. We keep doing this just to drive the point home that t is between 0 and 1, and what you multiply it by is what really makes the difference. So if we multiply it by diameter, hey, now we've got it moving down. Oh, but we ran into the same issue where we don't have a top row of circles to come in to complete our illusion. The way that we can do that, we're starting at 0 here, which is the top of the screen. But if we actually start -1, that's actually going to start above the screen, right? It's going to give us a negative value for y. So we're actually going to be drawing a row of circles above the main screen, but they're going to move down over time. Cool. Now I've got this infinitely looping sphere grid. Again, like we can play with moving a whole bunch of something around and just figuring out the distance that we move for each element to move to where its neighboring element is. If you can figure out that distance, in this case it was the diameter of the circle, you want to move it down 1 full circle width, then you have a loop that seamlessly loops. That's one of the secrets of the loop. Cool. So we'll take, actually, let's take another break here, I think. Do a quick, I guess, I meant to check and see if people found the breakout rooms useful. So if you have any comments on that, please just drop it in the chat. But yeah, let's take another quick maybe time check here. So we've got 50 minutes remaining. Yeah, let's do another quick 10-minute breakout room. Everyone can take a moment, absorb, talk about anything that they've found interesting or confusing, or maybe take a break, go get some water, go to the restroom, whatever you need to do. And then we'll come back here in 10 minutes.
Okay.
All right.
Oh, you came back. Cool.
Sorry?
You came back. Yeah, it
Okay.
just automatically puts everyone in one except for me, I guess.
Is this part also live streamed where we're just sitting here talking to each other?
You can only see this room, I think. So this is on live stream right now. Unless you want to not talk. And then I recommend you can't. You can just turn off your camera and take a break for a minute.
Sure, yeah, I'm going to go refill my water bottle.
Little refill.
Yep. have to say definitely the hardest part I knew it was going to be about teaching remotely is just having no feedback.
Yeah, and it's yeah. I think if you're teaching more and it's not like this one-off live stream workshop thing, like if you're teaching a series, you know what I mean? Like that was week after week, it gets better. Because I've been doing that as people get more comfortable. But I think for some people, this might be the first time they're doing a workshop in this way, and everyone. It's either like I think when this whole thing first started, like the students were like excited when I did the first round of immersive about learning online because everyone was scared and we were all trapped in our house, and now people are like fatigued. To where I was like, please turn on your camera or you'll never meet anyone. So it's just it's also like if everyone's working and you're on Zoom all the time, it's kind of like you get Zoom fatigue.
Yeah, Zoom fatigue is very real.
Yeah.
I've been interviewing for a job for the past month, and I've been on Zoom every single day, all day.
Oh yeah, I mean, and then there's also those things you can do if you say like a thumbs up, thumbs down in the on the chat or in the participants. There's like, I don't know if you see that. I see it because I put the participants in the chat in my sidebar, and I have this like coffee, thumbs up, thumbs down, break. That is one way you can do, but as any class, people get more comfortable over time. It will change, but yeah, it just depends. I don't know. When were we supposed to come back?
10 minutes.
When I don't remember when it started. And I don't think these. Oh no, they are timed. Okay, good. There is a timer. I just said redo it, and okay, good. We have 5 minutes left.
Yep.
There are some people back in here. It looks like.
Yeah, it looks like I'm running about 15 minutes behind where I thought I was going to be, but I wanted to spend more time on the actual producing concept parts and coding parts, because the end parts are really more references, like go take a look at this and this and this, and it's something you can kind of do in your own time afterward.
Mm-hmm. Yeah, I do the same thing with like giving them the slides and clickable slides, and then I can give everyone the live stream link, and they can try to go through it again if they need.
Yeah, it's exciting that we have it recorded. That's cool.
Yeah, I think it'll be helpful, and yeah, it's good.
And I got to figure out
I'm doing that now with the classes or regular classes too. So in case people miss class, it's super helpful. And also I think it makes more. I think it would be harder. I have no idea what's going to happen when we're like mixed in classroom and virtual, because it makes a lot of sense to be teaching and recording stuff via Zoom through live stream, like, or in this way, but it's going to be much harder and weirder to like, if you're teaching with like 5 people in a room, then 10 people remote, like, I just don't know how that's going to all work.
Yep.
Or if it will work. I just don't know. Yeah, I'm not sure. And who even knows when we'll be able to all hang out in a room together anyway, but I'm hoping in my lifetime. I'm hoping I'll live long that the pandemic will end and also be alive, and then we'll see other people in person again. And I'll teach in a classroom.
That was my first thought when they introduced lockdown. I was like, okay, and then what?
I know. And then what? What do we do now? I don't know. I think it could last like 2 more years. That's my feeling.
I mean, I feel similarly. People are very optimistic about the vaccine, and I don't know. I foresee at least a year. And companies, especially tech companies,
are normalcy. My sister works in research at Cedars-Sinai, and she's the person that approves all clinical trials for COVID or works through the process. So I always get updates from her about what's going on in the clinical trials.
Oh, wow, okay.
And there's, I think, 3 or 4 going on. And the way the pharmacies work is they kind of do different like they'll do clinical trials at a few different hospitals, but theirs is a major research hospital. So like remdesivir, which is the drug they're giving to people now that's antiviral to lessen the symptoms, was clinically tried there first. So just from knowing her and talking through the process of clinical trials, that's one of the reasons why I'm projecting the 2 years to go through clinical trials, to get an FDA approval, and then for distribution of a drug, it's going to take probably that long, I think.
That's what I would have thought too.
Yeah, I mean, and they are trying to speed stuff up, like within her work. They're like making it be more like only do cancer and COVID or whatever. They're just like really focusing on it. But at the same time, you've got to still follow protocols and make sure people are safe and do things in the right way, or the drug that they get could not be safe. You know what I mean? Like it could have adverse effects. So yeah, you don't just like concoct some bleach and drink, you know, you like you use science.
Who would have had that idea?
I don't know. Yeah, but remdesivir, the drug that is being used, was used through a clinical trial, which went well. And that's why it's being used on the leader of our great nation right now. So yeah, that's exciting. But either way, at least we can still do remote workshops. And if you're going to teach anything remotely, code is a great thing to teach.
Yeah, I do feel grateful to have been in a relatively pandemic-proof industry.
Me too. Yeah, I used to do theater. I was like, I already could see the tide turning when all the tech companies closed down all the theaters in the Mission and in the Soma area. And then I was like, okay, I'm going to start doing this stuff. Which is a smart move.
My brother was in entertainment. He did lights for big bands, and that industry is vaporized. So now he's also learning to code.
Yeah, that's cool. I studied lighting in college as well. Theater lighting. It's fun. You must do it too. Do you do DMX for your?
I've had to learn it within the past year. So I had to. My first project was for the temple, actually, for Burning Man. Because I was up until that point, I'd just been using addressable LED strips. That was my first time using actual like stage lighting, DMX lighting.
Much easier.
It is
easier, but it like works so much better. I just did a big installation. It was like a disaster with a million addressable LEDs, but I took a workshop and I know the DMX is better, but it's so expensive. So yeah,
there's a lot more tools that are DMX compatible for sure.
Yeah, I just think like it's more foolproof and better.
Yes.
What is that company? The Digital Ambiance. They did a workshop.
Oh yeah, they're amazing.
Yeah. Wow. We did DMX, but it's like the controller was like thousands of dollars. So we all had to take turns plugging the little things we made in, you know.
Yeah, he did the Matrix one.
Yeah, a gray area.
Yep.
I put it on with Rob. Yeah, he was a great teacher. It was super fun.
Nice. Yeah, he's really cool.
Yeah.
All right. It looks like we have people filtering back in.
Back.
Boop. Are we all back? Are the rooms officially closed?
I closed them.
Okay, cool. We're back. Welcome back. I hope you had a refreshing break. Hope you got everything done that you needed to do, whether it was dig into the code or go to the restroom or get some water or take a deep breath. Cool, so now we're back here. Let's go back to the slides. Actually, I should probably share my screen. That would help a lot.
It's shared.
Yay, all right. And I'm still logged in, thanks. Cool, so now we're gonna take a look at another technique that I call cascading. This is not an official term. I don't really know what to call it. I've heard people call it phasing as well, because you're changing the phase of a function across elements. But to show you what I mean, here's an example from bees and bombs, where you see like, let's take a look at this. This is a fun exercise. If you look at an animated GIF or some loop and you want to figure out how it was made, let's try and break this down. What we see is we have it's a hexagonal packed grid of circles. And those circles are just animating from a smaller diameter to a larger diameter, which is very similar to something we looked at earlier. But the difference is they're not all animating at the same time. They're actually offset. You can see this has this ripple effect where first the thing in the middle starts to be impacted by the animation, and then it moves outward. So that's what I mean by cascading. We're taking some shape, the circle, and modulating it by, in our case, a sine wave. That's what we'll take a look at. His wave is it's a modified sine wave with a break in the middle. And we're going to affect how it moves across a matrix or an array of elements. So let's draw a matrix of circles. We've already done that, but that's handy, whose sizes are modulated by a sine wave that cascades diagonally. I don't know a better way to word that. If you have any advice or suggestions, I'm open to it. This is an awkward wording. But that means I want the apparent movement to be diagonal. So whereas in this one, it's radial coming out from the center, we want it to kind of move from the either top right to bottom left or top left to bottom right. So let's take a look at how we might do that. Let's see if we go back to what we have. We've got our matrix of circles already. Cool. But we don't want it to move anymore. So let's take out, or at least we don't want it to move in that way. Now, hopefully, yep, we've got a static matrix of circles. And then we wanted to modulate the size, okay? So, well, we want to modulate it. We can modulate it by anything, but we've been modulating things by sine waves, so let's take a look at that. We're going to go within our, this is the part of the loop where we actually draw the circle. And, sorry, I'm moving code around. There we go. So the first thing we want to do is let's get our sine value, right? So this is the same pattern we've seen over and over again. We take t and multiply it by 2 pi because that means throughout the duration of our loop, which runs from 0 to 1, and we keep driving this home, this is our playhead from 0 to 1. And as we run through it, we want the values, the inputs into sine to run from 0 to 2 pi. So we multiply that. Got our sine value, and then we saw that we could change the diameter by mapping that sine value. So let's get the draw diameter. So we've already got something called diameter, which is how big, like the maximum size we want this circle to be. Let's do draw diameter. So this is how big we're actually going to draw it. So we're going to take map, again, a really useful function, map the sine value from -1 to 1. And then let's map it from 0. So at its smallest point, it's going to be 0. Basically, it's not going to show up. And then its largest, we'll do diameter, which is really max diameter at this point. And we'll draw it that way. Let's see what that does. Cool. Now we've got a matrix of circles that are all modulating in size by a sine wave. But they're all doing it at the same time. We don't have this cascade effect. So how can we cascade? Well, let's see if we can talk through how that might work. We want each of the circles, I'm going to pull the circles up again. I'm going to try to pull the circles up again. There we go. We want them to all be at a different position on the sine wave, essentially. What do I mean by that? So actually, I wish I kept open my visualizer of our, oh, it's not going to save it, oh no. Okay. I wanted to keep open our visualizer of the sine wave. Let's run our sketch. Cool. Right, so we can actually visualize this as this is running. As it runs from 0 to 1, it goes down to where the diameter is 0, and then it goes up, and it goes up to here where the diameter is, whatever that diameter is, I think 50. And it's based on the position on this sine wave that determines the diameter of the circle. What we'd like to do is actually distribute the circles across the sine wave so that for a particular sine wave, we're at a different position on the circle. essentially we want to shift the sine wave left or right. We saw that we could do that by adding a number to the thing that we pass into the sine wave. We saw that in our visualizer, which I wish I had kept open at this point. But if we go back into here, so if we push over in here, in our sine, when we call sine, we want to add something, right? And we want to add it, the thing that we want to add is going to determine how the sine wave shifts. So what if we just add x, right? So we're going to shift the sine wave based on the position, the x position of the circle. Wow, it turns out that does it. So yeah, let's look at what's happening here. Right? We're taking the x value of the position of the circle and pushing that, or adding that, basically pushing the sine wave over. So that for this particular call, for this column of circles, the call to sine is going to produce a slightly shifted value than the one next to it, because the x value is different. Right? So you want to think about how we visualize the sine wave across this matrix of circles. If we wanted it to do it diagonally, well, actually, let's do it vertically. We just add y. Now we're shifting it vertically. And again, we've got an infinite loop because of our t times 2 pi, which is really handy. And if we want it to do based both on x and y, we can add them both. Yeah. Now we got like a pretty compelling animated GIF here, where it's this cascading effect from top left to bottom right of the circles. So the main takeaway here is if you want to modulate a sine wave across a set of something based on the position, you can just add those positions to the thing that you pass into the sine. That's the main takeaway here. That's that plus c that we saw in the sine equation earlier. Cool. So you've probably seen this. This looks like a loading spinner that you might have seen on a website, waiting for it to load. The principle is exactly the same. We have a bunch of circles. We want to change their size. This column, each of these is modulated by a sine wave, from smaller to larger, but it's spread across this the circular distribution of circles. So can we do that? Let's give that a shot. This one's going to be a little bit math heavy, because we actually have to figure out how to position those circles like they are on a clock. But we can use the relationship that we saw in of sines to x and y in an angle to do that for us. So let's start over. We're going to draw some circles. We're going to draw a ring of circles instead. And we don't need rows and columns anymore. We just need the number of circles, so our circle count. And let's say 12 circles. We want to evenly distribute 12 circles around a larger circle so that it looks like the numbers on a clock. And what else do we need to know? We need to know how big is the clock, essentially. Let's call it the ring radius. Let's say that's 150. And then we need to know what's the maximum diameter of the circles that we're drawing. So let's make that into a circle diameter of 50. And you'll see why I'm using radius for one and diameter for the other in a minute. I'm going to introduce a quick function here just to make our lives a little bit easier. That's the translate function. What translate does is it changes where 0, 0 is. So, by default, 0, 0 is up at the top left corner. If we do translate width times a half and height times a half, so that's telling us the new value of 0, 0 should be the center of the screen. So just to prove that, let's draw quickly a circle at 0, 0, which we would expect originally to have been centered at the top left. But now we should see it's actually centered at the center of the screen. It's because we called translate. So remember, translate, it affects everything after it. Some other functions that work with translate are push and pop. Basically, push says start a context in which you can make changes to translate. You can call translate, you can call stroke, fill, all the changes that you make that actually make changes to all the way your code runs afterward are saved when you say push. And then when you're done with all of your changes, if you go pop, it's going to return the state to what it was when you called push. So if you're a software engineer and you're familiar with stacks, it's pushing a display context onto the stack and then popping it back off. So that allows us, it's pretty good practice anytime you're calling stroke or fill or translate to just wrap it with a push and a pop. That way you know that those changes are isolated here, because otherwise they can start affecting different areas of your code, which can be very confusing. But that's a little bit aside. Let's go back to what we were trying to do, which was draw a ring of circles. So we've got our 0, 0 now is centered at center of the screen. We need to figure out how to position a bunch of items radially around a circle. So we're going to need to figure out a way to, let's do that by iterating through the full circle. So the way that we could do that is start at an angle of 0, which would be on the right, and go all the way through 2 pi, which would be a full rotation of the circle. And let's subdivide that, that distribution of angles by the number of circles that we want to go. So let's, for each of the circles that we want to draw, we're going to use our friend, the map function again, to determine the angle, right? So we're going to take the full range of angles which are available to us from 0 to 2 pi, it's a full circle, and we're going to map the I value from 0 to circle count. That's going to evenly divide the angle, or the circle, into angles that match the number of circles that we're trying to do to distribute across it. Right? So now we've got an angle for a particular circle. We want to figure out the x and y coordinates of that. Again, if we take a look back at our visualization, I'm going to pull that up real quick. Given an angle, the angle of this here, the x-coordinate is the cosine, and the y-coordinate is the sine. So we have an angle. If we take the cosine of that angle, we're going to get the x-coordinate. If we take the sine of that angle, we're going to get the y-coordinate. And then the radius is the amplitude. So if we take sine of an angle times a radius, we're actually going to get the position on the circle, which is super handy. This is why trigonometry is really cool, because you can really use it to draw things, distribute them, really, or to use the techniques to put things onto a screen. I think it's pretty cool. I'm maybe a math nerd that way. So we want to get the x and y coordinates. So what did we just say? We said that the x coordinate is the cosine of the angle. I'm going to leave off the radius for now, just so we can see what that looks like. And then sine of the angle. Let's just draw a circle at that position. So remember, we're iterating through this. We're going to draw it a circle number of times. For each circle, we're going to figure out what angle it should be around a larger circle. We're going to get the x, y coordinates, and we're going to print out the circle there. So we're going to say circle diameter, which we saved. Again, our radius is basically 1, so they're all on top of each other. There are 12 circles there. But if we multiply it by our ring radius, now we've got a nice distribution of circles around a larger circle. That's pretty cool. That technique right there is extremely useful. I use it all the time. Feel free to come back to it for any of your own work. But now, what did we want to do? We wanted to modulate the size, and we wanted to cascade it across this range from 0 to circle count. So we're going to, again, get in the habit of doing this. We're going to basically take the sine value, right? 0 times 2 pi again. Okay, we need to figure out what our offset is. Let's finish this first, and then we'll take a look at the offset. So we'll do the same thing, draw a diameter. We're going to map our sine value, -1 to 1, 0 to diameter. So you can see this is kind of a recipe that we can use over and over. We call it circle diameter, sorry. Right, so now they're all modulated at the same time. we want to cascade. So it means we're going to have to add some value to the thing that we pass into sine. And in this case, what is it? We want to move around the ring of rings, or the ring of circles. So we could do that by the angle. The angle probably is a good thing to have there. And look at that. We've just recreated a loading spinner. You can, rather than going on some website and finding one, you can write your own and process it. Cool. I think that's pretty neat. So yeah, that was a lot. I know we covered a lot of math there. The relationship of sine and cosine to an angle and the x, y coordinates on the circle. I want to take a quick pause, check the chats. Looks like the chats have been pretty silent so far. Cool, so yeah, to a quick time check. We have 20 minutes left. I am definitely behind now, okay. So I might, I've got several animating color exercises. Maybe I'll just focus on a couple of them, just so we have time to get through the stuff at the end. But so far we've been doing everything in black and white. What if we wanted to do some stuff in color? You know, we took a look at all of the coloring things that processing has to offer. Let's animate smoothly from black to white. Right? That's not going to be that different from what we've done so far. We've been animating size on a sine wave. Let's animate color on a sine wave. So we've got all this stuff for drawing a ring of circles. We can just get rid of all of that. Let's start over again. Again, we start with the same building blocks of our normalized time and a animation function that takes in normalized time. And this time we're going to draw a fading circle. And again, we're going to be changing the styles, so just get in the habit of using push and pop anytime we change styles so that you're not confused later, because we're going to be changing the fill value. So let's just start by drawing a circle at the center. Give it a diameter of 200. Cool, it's white. We said we wanted it to be on a red background, so where we're changing the background, instead of passing in 0 for black, let's make it red. So 3 values is RGB. Remember way back at the beginning we talked about colors? Let's make it all the way red, no green, no black. Cool, that's lovely. Hurts my eyes a little bit, but cool. So now, let's also get rid of the stroke. I don't like that black stroke. All right. And we want to animate the fill of this. Okay, so first we're going to be making some change to the fill. We know that. Let's pass in some fill value. And we want to do it with a sine wave. Now, this is probably looking pretty familiar by now, hopefully. Sine times 2 pi. I'm going to do a full sine, full wavelength of a sine throughout our animation. And we're going to use it to get a fill value. I'm going to map that sine value, -1 to 1. And now the range of values that we care about are 0 to 255, because 0 would be black, 255 would be white. And then we take that fill value, pass it into fill, and then everything we draw after that should be filled in that color. Now we've got this pulsing black to white thing. This is pretty cool. Another, just to point out the power of map values, we don't have to do 0 to 255. We could do 0 to 128, so we don't go all the way white. Just go black to gray. It gives us some knobs that we can change to really affect the final output. And that's really what all of these exercises is about giving you tools to have knobs to change in order to have control over the output of your loops. Cool, so back in the slides. Well, what if we wanted to do more than just gray? We've seen pretty clearly now how we can animate a particular attribute with using sine and cosine. We could do that by animating each of the red, green, and blue. I don't know why I kept getting these ordered wrong when I was writing these. Red, green, and blue. I'm going to change that. But it's kind of hard to reason about how much should we change red over time, how much we should change blue. You can do it and see what you come up with. But we do have better options. So you can blend between two colors. So there's a built-in function in processing called lerp color. Lerp is a funny word. It means linear interpolation. It means to interpolate smoothly from one value to another using a normalized value. Normalized values are really useful. So I have a coding exercise for this one. I think I'm going to not go into that, do the coding exercise, but I'm going to show you the demo just to demonstrate how lerp color works. So what I've done is I've created two colors. I just picked these randomly from a website that generates random colors. And I'm moving my mouse using mouse X, and I'm mapping. Let's take a look at the actual code here. I'm using a function called norm, which is a special version of map. It's basically the same as doing map mouse X from 0 to width. It's basically hard coding the last two to a range of 0 and 1, exactly the same. So if you want to normalize something, you can just leave off those last two from map and just use norm. But what this is doing, you can see the number, over here, norm is 0 because I'm at the far left. And as I go across, it's 1 when I'm at the far right. And you see, look at the color of this bar. You can see it's smoothly interpolating between this color on the left and this color on the right. And that's happening via lerp color. Where I pass in the first color, I pass in the second color, and I pass in the normalized value for how far between those two colors we want to lerp. So that's how lerp color works. I'm going to skip the coding exercise that uses lerp color. Oh yeah, I mentioned norm. So this is a special case of map. I already called this out. It's basically hard coding the ending range from 0 to 1. It's worth noting that the return values are not clamped. So if you get this start and stop range wrong, your norm values might actually exceed 0, go to negative, or go above 1. It's just something to keep in mind. So yeah, we could use lerp color to animate smoothly from red to green. It would be very similar to the one we just did for black and white. But another way we could do it is we could change color modes. So we could blend all the colors. There's another color mode. Earlier I said when you use colors in processing, by default they're RGB. But you can actually call this function color mode and pass in HSB, which means hue, saturation, and brightness, which is a different way of specifying colors. With RGB, you're specifying how much red, how much green, how much blue. With hue, saturation, brightness, you're specifying the hue on a rainbow of colors. Saturation, how much of that color should be present. And then brightness, how bright is that color? So it's a little bit different way of reasoning about colors. The cool thing about it, though, is that now we have a single value that we can modulate in order to get a rainbow. And everybody loves rainbows, so I can't skip this one. So we're going to draw a circle that animates across a rainbow on a black background. And this one's actually, because of color mode, it's actually really quick. So let's keep what we had here. We're going to be drawing a fill value, right? We're going to be drawing a rainbow circle. Cool. And we're also going to, in our setup, just change the color mode to HSB. And then when you change color mode, you can also pass in the new ranges. By default, it goes from 0 to 255. With HSB, I think it's like 360, 100, and 100. 360 for the hue, 100 for saturation and brightness. This is going to say all of these values are going to be normalized. So hue, saturation, and brightness all run from 0 to 1. It's going to be really handy. So let's start over here. Again, we're drawing our circle in the center. We've got our fill value. We're going to determine what our fill value should be. It's going to be a color. And it's going to be a color let's just see what happens if we do 0, 1, 1. So it's going to be full saturation, full brightness, and whatever 0 is on the hue. Turns out 0 is red, okay? But if we use t, which runs from 0 to 1 over the course of our loop, that means we're going to cycle through all of the available colors. And we've got a rainbow. That's really fun. I think that's pretty cool. And that comes in really handy, especially if you want to cascade with the rainbow, and you get some really fun effects. Cool. We got 12 minutes left. Oh my goodness. Yeah, I'm about 20 minutes behind, so there's gonna be some stuff at the end that unfortunately we're not gonna get to cover, but most of it is pointers in directions of resources for you to check out on your own anyway. And I will also be available on the chat to answer any questions you have afterward. Boy, this could take the entire remainder of the course actually. Yeah, I'm not gonna do the coding exercises for noise then. Apologies for that, but we'll just take a look at what it's capable of. So noise is going to be one that you're going to have to play with. It took me a while to really internalize and understand what noise is doing. The good news is there are actually some built-in demo sketches in processing that demonstrate how noise works. So again, I mentioned in processing, you go up to File, Examples. It brings up this huge collection of topics for you to look into. Some of them are basics, like how to do programming, what are the basic functions available. Some of them are more advanced, working with data. This is really an amazing resource if you want to learn more about processing. But you see that there's these noise 1D, 2D, and 3D. So let's just run them real quick and see what they do. So noise you can think of as kind of a controlled, natural looking random. And it's a function that you can pass in a number, and as you change that number, if you change that number by a little bit, it guarantees that the resulting output change is going to be small and smooth. It's based on a function called Perlin noise, which was, I think it was originally made for the movie Tron, because Perlin and Dan Perlin didn't like the rigid look of computer graphics at the time. He wanted something more natural, and so that's what this is really good for. It's for giving you natural moving. It introduces some more organic movements to your sketches. Yeah, I want to make sure that we can touch on the other topics, and this one is definitely a rabbit hole. So I apologize for that. I do recommend that you go check out the Noise 1D, 2D, and 3D demo sketches. They're very enlightening. I'm going to skip the code along exercise that would make a circle modulated by noise rather than sine. That's the main takeaway here is, thus far we've been modulating by a sine wave, which is a very smooth curve. Noise is going to be a more chaotic curve, like a more natural windy curve. They actually use it in Pixar movies to simulate like the flow of grass or water as it moves, or clouds. It's really good at generating clouds. Necessary Disorder, he has a fantastic tutorial. He's an artist that I mentioned earlier on how to use noise to generate the kind of art that he does. That's kind of his signature, is this this organic looking, how could this possibly be a programmable infinite loop? This tutorial is everything I know about how to use noise came from this tutorial. It's a fantastic resource. I highly recommend it. I also highly recommend that you don't be discouraged at first. I read this tutorial probably 5 or 6 times, and every single time I was like, I don't understand what is going on here. It really does take a little bit of time and a lot of hands-on experimentation with it to really understand how noise is working. But once you do it, you can actually use it to create curves that look like this, like the Joy Division album art. If you take a look at the basics math noise wave example in processing, it shows you how to draw one of these waves. So if you draw a whole bunch of them, you could quickly generate an interactive Joy Division album art cover. So let's recap. That's the end of the produce section, but there's a lot. So let me sum up. We can control our loop's playback and length using this loop normal function that we derived, where we pass in the current frame based on frame count or based on mouse X or some other thing, and the total number of frames that we wanted to take. And it's going to give us back a number between 0 and 1 that we use as our playhead. We can modulate parameters using repeating functions like sine. And if you do sine of t times 2 pi, you're always going to get a full cycle. So you can just multiply that by stuff, and you'll get interesting results. Just play around with it. You can map that value from, in our case, from -1 to 1 to some other range that would be useful for your use case. We looked at some secrets for generating loops. And using repeating functions is a really good way to do that, sine waves. Or we could simulate infinite movement by having an infinite collection of objects where each one takes the location of its neighbor. We can cascade functions across a collection of objects to get that cool wave effect. We can animate color using lerp color, or if you want to go rainbow mode, you can use color mode HSB. Noise will introduce some color, controlled randomness to the motion. So that's the end of produce. Okay, we have 5 minutes. I budgeted about 10 or 15 for this section, so we're going to rush through it for polish and package. So polish, there's no coding exercises here. This is just going to be introductions to concepts. We're going to look at blend modes to get more dynamic colors, easing to change rate of motion over time, and motion blur to make a prettier output. And these are all techniques. You know, I was making GIFs in processing for a while, and like I said, I kept getting frustrated. I would see other artists and like, wow, their stuff looks so much better than mine. Why does mine look so mechanical, like it was drawn in processing? And these techniques are really the key, in my mind, to how to get your sketches looking more organic. So blend modes. You're probably familiar with blend modes if you've used other graphics editing environments like Photoshop or Illustrator. It determines how colors interact when you add them to the canvas. So we can change them in processing with the blend mode function. And it works just like stroke and fill. You can push it and pop it. So if you change blend mode within a push, you can pop it and it will change back, which is useful. There's a whole bunch of values for it. They are all defined. These are all the descriptions from the processing documentation. Again, if you're probably familiar with these if you've used Photoshop or Illustrator. The one that I find most useful is additive, add. The reason that is because light is additive in real life. This is how we're used to color working when you look at color, like imagine colored glass. When you look at two pieces of colored glass on top of each other, the additive, or the effect, the way that those colors blend is an additive effect. So I use blend mode add in almost every one of my sketches. And take a look and show you the difference. So we're using that rainbow thing that we looked at, we're cascading it across circles. With blend mode blend, which is the default, it just means that whenever we draw on top of something, it just literally means that we're drawing on top of it. So you can actually see the order in which these circles were drawn. This one right here was the last one drawn because it's on top. With blend mode add, the colors actually blend together and you get this really, I think, more attractive output. One thing to note with add, you're going to want to decrease the brightness on your colors, because if it's already at brightness 1, you're already going to be at full brightness, right? If you add 2 full brightness colors together, you're just going to get white. So in this example, each of these circles is dimmed to about half brightness. So yeah, you can see that it looks like these are now pieces of colored glass. You can't really tell which one was drawn first. And I use it in so many of my pieces. Like this is just a sine wave with blend mode add, right? They're very dim sine waves, and we use blend mode add to get that cool glowing Tron effect. This one too. This one is a combination of blend mode add, of cascading. So I've got a whole bunch of very small dots on here that we're cascading around. And then I'm modulating the position of those dots and colors by sine and by noise. So it's all of these techniques that I just showed you thrown onto one piece. And that's kind of my goal for this entire workshop, is really to show you this toolbox of functions that you have available to you to generate interesting content. Put it together in interesting ways, and you'll eventually land on an aesthetic that you like. Easing. So easing is something that you are definitely familiar with, even if you don't know it by that name. You've been seeing it throughout this presentation, in fact. It has to do with changing the motion, how motion changes over time. So most motion, all of our motion so far has been linear. Like we start at one point and we move at a constant rate to some other point. In real life, no motion is actually like that. You don't just start at a single rate and continue moving, except for maybe like conveyor belts at the supermarket. In practice, motion changes over time. And the reason I say you're probably familiar with it is you can see it in this presentation. So as I move from slide to slide, it's actually using easing. It's not just going at a constant rate from one to the other. There's a smoothness, and the rate of change, or the rate of motion changes over time. So it eases in. This is an example of linear motion, moving straight from one point to another without any change. This is an example of easing. So you can see with an ease in curve, we start at the bottom and then it takes a while, and then we go up to the end. Ease in out, has curves at the beginning and end. And ease out, which is how the slides are actually moving in this case. They start off fast and then they approach their goal slowly. Now in this case, this curve is sinusoidal. There's so many different kinds of easing functions. Take a look at it. There's all these curves. There's a bunch of libraries that are available for you. There's some built into processing, in fact. I recommend taking a look at this page, Robert Penner's function. Robert Penner is the pioneer. He came up with the way to express these. And there's a tutorial on easing functions and processing here. There's also the Robert Penner's has examples in pretty much every programming language that's in current use. There's also some that are built into processing. So if you go to the libraries, Sketch import library, you can add libraries that will add functionality to processing. And there's an easing one, so you can just drop that in and get your easing for free. The last polish, we have 1 minute left, is motion blur. Motion blur, thus far, we've seen all of our motion feels kind of computery. And that's because we're drawing each frame as a straight line, and then we draw the next frame. So if there's any change in movement between those two, it's really a quick cut. There's not really that blur, which you get in real life. If you're watching an object move really fast, because of the way our eyes work, we have this persistence of vision that makes a moving object appear to blur. So it's a really quick and useful technique that you can add to your processing sketches to make them look nicer. And this was one that confounded me for a long time. Before I knew that this was what the difference was, I would just see sketches that used motion blur and be like, I don't know, it just looks better. I can't tell why, it just looks more real. And you can tell this is a sketch that I did a long time ago where this was my first take on it before I discovered motion blur. And you see the in between frames, it just looks kind of choppy. And here we actually are simulating motion blur. I'm not going to dig into exactly how that works. I'm going to give you some code that does it for you, and then you can dig in as an exercise to the reader. It took me a long time to understand how it works, but the cool thing is it's a magic recipe. If you just use it, it will make your sketches look better. But you can kind of see that the edges blur in between frames, and it just looks a little bit more realistic. Cool. So this really is the culmination of this workshop is this template. If you click this link to the GIF template, this is the template that I use to start every one of my processing sketches. It was originally written by Bees and Bombs. I've modified it a little bit and put some comments in there to tell you how it works. It includes motion blur. There's a necessary disorder tutorial explaining this template. It's a really popular template within the processing animated GIF loop community. So I highly recommend just take that, dig into it, ask me any questions you have about it in the chat afterward. This really, if you get nothing else out of this class, take this template. That's your takeaway. This is your swag for coming to this class.
Thank you.
Yeah. Oh, so quickly package. There's some tools. Here's some tools. Go look at them. This is how you generate. Once you use that template, use these tools to turn them into a final GIF. And I've included the commands that you can run in each of those to generate those GIFs. And
also,
then,
Giphy Capture is my favorite.
Yeah, there's a ton of tools. These are just the ones that I use. I'm biased towards command line tools because I'm a software nerd.
Yeah, and I'm a visual designer, so those of you that I like the command line, but if you want to do something real fast and you just want to grab it, Giphy Capture software is great for Mac. I don't know if it's on PC.
Awesome. Yeah, if you send me that link, I'll add it to the slides so that everyone can have that later. Then we've got resources, a bunch of links for community, a bunch of links for artists that inspired me and hopefully will inspire you, and a bunch of tutorial links on how to get better with processing and this stuff in general. And with that, thank you. We're only 3 minutes over. Thank you so much. I hope you got something out of it.
It was great. You got a lot out of it. I whenever I teach P5, I'm always like, and math. And then I'm like, yeah, I thought you did a great job at describing the sine waves, cosine, and all of those easing functions.
Awesome.
They're great. And also, that's a very cool resource you gave us for the math piece, which I forget what it was called, but I saved it in my tabs.
The graphing function, the graphing calculator, decimals.
Yeah, super helpful.
Yeah, that thing is amazing if you want to just take some piece of math and explore it. That graphing calculator supports more math than I will ever understand.
It's like when we used to have those TI, what was it, 89?
TI 89, yeah.
TI 89, we're probably the same age. Yeah, you had to have it if you're in advanced math, and they're so expensive. My mom was like, why do I need to get you this? And I don't know. Yeah, but that's what it reminds me of.
Yeah, this is like the TI 89, but plus, 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 plus. It does so much. It's so cool. I'm geeking out about it. It's an incredibly powerful tool. I recommend you dig into it. But yeah,
this is great. Oh, let me, before you guys go, let me put the live stream link in here so you have it, because I don't know when I'm gonna do it, when I'll send it out. I have to take a day off. So let me give it to you now. So that's the link to the live stream, which will be, the recording of this. Just so meta. So maybe I'll stop live streaming right now.
I'll also take that link and I'll attach it